Hello, everyone. Welcome. It's My name is Muriel Medard, and I'm delighted to be welcoming you today to this Section 4 Wireless Networked and Distributed Systems with two fantastic co-panelists, Heidi Hammer and Matt Spellback-Sharp, whom I'll be introducing later. So with that, if I can ask to share the slides. So as I've mentioned, this is the session 4 wireless network and distributed systems. This is part of our MIT Climate Implications of Computing and Communications workshop. Next. Just to remind you, this is where we're at. So please do go to our other sessions if you're able to today and after this one. Next. Okay, so let me just quickly set the stage as to why we're looking at this issue of climate implications. And let me remind you a little bit just about the evolution of our networks. We think right now of 5G and so on. Every 10 years there's been another evolution of networks. But originally it was basically a wireless edge, some D2D, some device to device, maybe with a Bluetooth, and then some fairly centralized repositories of data. And it seemed just like magic to be able to really access the data wirelessly. The feedback was very, very small in effect between the sender and the ultimate repository of the data. And the repositories of the data were just in effect connected through the backbone. Moving on, next. We just start seeing, thank you. We're just seeing a lot more storage, and also a far more distributed type of setting with initially technologies such as mirror sites, which in effect, which now of course completely a commonplace, but in effect, distributing the data inside the network. This is sort of the first integration towards getting storage and the network joined together with attendant issues now with data centers and the very large use of energy that they entail. So, and of course, attending large OPEX. And now when we go to the next stage, thank you. This is becoming now that, let's say that this is already sort of the 4G sort of the more advanced version of 4G, earlier versions of 5G, you now have a cloud, which is really an extremely distributed system. You now have, of course, much more computing, in particular cluster computing. You're using the network not just to retrieve data from someplace or just to have, conversations and point-to-point data, but you're really using it for a lot of services which entail more and more computing. particularly with the advent of machine learning being incorporated into many of the services, then that has to happen at the edge or in some location where it's being offloaded. So we're seeing cloud storage, but also cloud computing increasingly. We're seeing also with the advent of more and more high frequencies, often called millimeter wave, because those frequencies are in parts of the spectrum which is very plentiful in terms of bandwidth. We're seeing more deployment. Of hardware, both because you need hardware to access these new frequencies, but also because these frequencies tend to be much more localized, don't not travel quite as far, and therefore they require more of a footprint in effect to have coverage. And then if you go to the next slide, you add another layer here, which is IoT. So now you have, a very dense, rich fabric of devices which are talking to each other, which are also talking with the rest of the network, and increasingly coverage through systems such as satellite. Many of us who follow what's going on in industry right now see that, for instance, the explosion of low Earth orbit networks is really changing how a lot of the coverage is being done. So what's happening is we're not really having a substitution, say, of transmissions at traditional frequencies with just a different technology, improved technologies. We're seeing evolution of what was there before, as well as constant addition of more and more hardware, more and more services. Now, what does this mean in terms of sustainability, in terms of climate impact? Well, and the other question, of course, is, for forums such as ours today, what can the intersection between academic research and industrial know-how bring together? And I just wanted to give you just a couple of small vignettes from my own work to illustrate what can be brought together, and then I'll try to frame the questions and go to our panelists. So going next, here's an example of some research that was done in my lab. This was research that had been sponsored by Nokia, done with them. And, we're looking, for instance, at the cost of infrastructure. And when I talk about cost, I don't just mean the capex of laying out the infrastructure, and of course, the cost of having made that infrastructure, but also the considerable OpEx of having that infrastructure up and running. The cost of just having, say, a base station on is far more important than just as the cost of any particular transmission. And typically what's happening is that infrastructure is more and more being deployed, not for coverage, which is, say the circles that you see here, there's enough coverage. It's really in order to accommodate more users. And here's one example, just because my lab is the Network Coding and Reliable Communications Lab in the Research Lab for Electronics. So we do considerable work on network coding. Current systems, for instance, right now don't use network coding. And you can see is that the cost of deployment is much higher. Here's the number of base stations. And you can see, that the red lines are, basically what people are doing now. And in effect, if there was just more judicious use of the existing resources, you would have to deploy fewer base stations with the attendant benefits in terms of carbon footprint. I just want to bring to your attention something funny here, which is, in some cases, actually, it's better to give people better quality of service, because by giving them better quality of service, faster rates, you actually get users off the network faster. And by getting them off the network faster, you're actually able to service more users with the same infrastructure. So, there's some very interesting and subtle interactions. Just to give you another example, going next. A lot of it is of the research we've been doing currently is around the cost of equipment. We have all heard about chip shortages. If you look at current systems right now, you have dedicated chips or at least parts of chips for all the different error correcting codes, which are codes that are used to maintain the integrity, the reliability of the data, sometimes even for different rates of code. So you have this just plethora of different chips. One of the things that my lab in collaboration with the Hamilton Institute in Ireland has developed is something called GRAND, which is guessing random additive noise decoding, which gives you a single chip, and we have developed such a chip with Boston University, gives you a single chip that can decode all codes. So rather than having obsolescence of chips as new codes come in different standards, you can use one chip for all codes, and you don't have to have this, in effect, waste of ASICs of circuits. This is not done with industry. This is sponsored by DARPA and NSF. So moving on to the last slide. What is the scope of, of course, we'll have further discussion about this with our speakers. What is the scope? Is the infrastructure, a lot of infrastructure, generally turned on. The cost of that, a lot more hardware, often specialized, non-reusable, a lot more distributed systems, as you saw from the picture. So less visibility into energy use. Who's using the energy, who's actually incurring the cost of the energy. A lot more data, often transported for purposes of machine learning. For instance, if you look at a lot of the deployment currently, for instance, in the backbone of underwater fiber, it's actually for purposes of transporting data in the context of machine learning, not data that is meant for the end user. The cost is often not included in the planning. And how do we also consider the costs in a holistic way across storage, computation, communications, when many of these functions are now not being managed by the same entity, but are basically highly distributed and integrated across the entire system. So I'm very much looking forward to hearing today the thoughts of our speakers on this, and of course of the audience. And I'd like to start by doing so with Heidi. Heidi Hammer is Senior Vice President of Field Engineering at Verizon, and she leads the team responsible for rolling out Verizon's 5G network and also for improving its 4G LTE network. Welcome, Heidi.
Thanks, Muriel. It's nice to be here. So I think I'll start off just by kind of talking a little bit about what we're doing at Verizon from a green energy perspective, and then tie into actually some of the things that you said, Muriel. And why we feel very responsible for working through this, and not only for Verizon, but also for the industry as a whole, and for some of our customers, quite frankly. We also partner very closely with vendors, our OEMs, which you'll hear from one of our key partners next, from Ericsson, Mats Sharp. So if we could go to the first slide, please. So Verizon has been committed to tackling climate change since 2017. Very publicly, we announced a chief sustainability officer actually prior to that. And there were a couple reasons, and one of them you mentioned, Muriel, is that it's a tremendous amount of cost to us to run our network, not only to replace hardware as we continue to upgrade technology, but then also the OpEx of actually running that hardware and creating that customer experience. And that OpEx comes from electricity or any kind of energy source, but it also comes tremendous cost in cooling that equipment as well. And so we have been very much engaged with partners in supporting the development of renewable energy. We've become one of the largest corporate buyers of renewable energy. At this time, we're primarily using solar, wind, and also fuel cell technology in order to do that. We're engineers, so we're perfectly poised to attack this issue. We have a lot of metrics AI&D that we use, artificial intelligence, machine learning, data analytics to help us and set up quantitative scorecards that each of the engineering teams is expected to hit on an annual basis. We actually launched the first U.S. telecom green bond back in 2019. We have launched 2 additional bonds, $1 billion each, and for each bond that we issued, we allocated all the money that came from that in the following year. And that money gets allocated out to folks that have great ideas on how we are going to continue to drive the energy curve down, and also to renewable energy companies. 93% of the emissions for Verizon come out of our networks. And so we really look at what is the hardware that we buy, how do we operate that hardware, and then what can we do from an offset perspective? So can we use those renewable energy sources? And then also, can we participate in reforestation in order to get to a carbon neutral situation, which we've committed to do by 2025. So we are always looking for ways that we can move off of old technology like copper to fiber, or 3G. We're getting ready to shut down our 3G network, which is much more of a power hog than our new 5G network that we have out there. And so it's difficult to do that because some customers don't want to leave their copper lines, or they have devices that are 3G only. And so not only do we have to go out and touch our network and make a change to the actual infrastructure that we've built, which takes time, money, and energy of the people energy type, but we also have to change the devices that are out in our customers' hands. And when you think about how we use energy, it's everybody jumps right away to data centers, but it really starts at the device and the energy that the devices use, and then moves along to routers like your home web routers, your distributed networks, and then into the data centers and the hubs. And the devices are actually the least energy efficient out of that. And then as we get into the center, we get more and more energy efficient. We have been building our data centers, as a telco, where we started in our history. We really had large switching centers, and we've been moving more and more to more of a compute, as you said, Muriel, data center, to be able to have the centers be more energy efficient, able to use waterside economizers and evaporation cooling and new ways of making sure that we reclaim and reuse water that is used in our systems. And again, doing different aisle setups so that we don't generate as much heat from that equipment. Verizon also has the fourth, I think we are now the fourth largest fleet in the US, which is pretty amazing. And so because really our fleet is primarily in the Northeast where we have our Fios offering, but we look at ways where we can reduce gas consumption. We've gone to some hybrid vehicles, making sure that our technicians only use as large a vehicle as they need, that they're not out with a big bucket truck if they could go do the job from a van, for example, making sure that, we're using more efficient engines, et cetera. And then, as I said, we've invested in on-site green energy, and we've partnered with our OEMs. And again, you'll hear from Matt's after me, but we do a lot of work with Ericsson. Not only does Ericsson do a ton of research that we use, but they also partner with us and our planning organization to make sure that the hardware that they are making is as efficient as possible. And that we're moving towards virtualization at every part of our network, so that when we make these technology changes, we're not doing like for like swaps of all the hardware in order to get that energy consumption. Much more of the power will come from the compute and the software, which we will be able to utilize and spin up and spin down capacity only when we need it for demand. Muriel talked about our networks being on all the time. We are actually starting to look at like sleep mode for our cell sites, again, in the core, looking at virtualized capacity based on demand so that we don't have the network at full power all the time. We're really only powering up as our customers need it. So again, we've set I think I said 2020, but made it even more ambitious, but we are setting a goal to achieve zero operational emissions by 2035. So if we can go to the next slide, please. So I already talked about some of this. Our path to that net zero emissions really is to continue to do these billion-dollar green bonds, which we then put that money back into the initiative. We also have entered into these long-term power purchase agreements where we can get tons and tons, gigawatts of energy, renewable energy capacity, continue to install equipment that is very efficient. And so this is, a corporate target that we have set and have said very publicly, and we read out in our quarterly earnings on where we are relative to this. We can go to the next slide, please. I talked briefly about some of the limitations and challenges that we have. As I said, we're shutting down our CDMA network, but that has not been simplistic. We have a lot of customers that utilize CDMA, whether it's somebody that still has a 3G only phone, but really where the bulk of the usage at this point is coming is from IoT devices. And IoT devices are sort of a double-edged sword for us because a lot of them are 3G only. And so we've had to work with our enterprise customers to be able to upgrade them so that we can shut the network down. But on the flip side, they really allow us to do some of that machine learning that Muriel was talking about and to be able to provide services not only to help Verizon be more efficient, but to help others within our industry and other sectors. So IoT devices are used, for example, for smart grids for electric companies to make sure that they are having the most efficient distribution of energy. We use them to look for, power vampires anywhere where we see energy coming from one of our network elements that is, anomalous to what we would expect. And so then we can go and do some research into why is a certain cell site pulling more power than we would expect, or a data center line in the switch. So we also can give that service out to other sectors so that they can also utilize that. And we partner with the power companies as well to do some of that. And that's that innovation that goes beyond telco. The devices, as I said, actually eat up most of the power. And I loved what Muriel said. I'm going to go do more research into the GRAN chip because that definitely is an issue for us, is as we continue to upgrade the networks, devices need to be upgraded. The chips, more and more chips need to be in the phones and in home routers. And now we have a fixed wireless offering that allows us to give broadband to folks within their home at a broadband rate. And again, those chips will constantly need to be refreshed. Talking to our vendors, as I said, making sure that we are encouraging them to be as power efficient as possible because we bear the burden of that OpEx. We definitely are incented to do that. But we use a lot of industry bodies and standard bodies to help make sure that the entire ecosystem has aligned incentives to move us towards the zero emissions. And then utilizing, as I said, data analytics to make sure that we have visibility into how our network is operating and where there are opportunities for improvement in how we operate them to be able to be more efficient. And then I believe that was it, but can we go to the next slide? Yes, that is it. So that is what I have, and I'll hand it off to Matt.
Thank you.
Back to Muriel, sorry.
Thank you through Muriel. Thank you very much, Heidi. That was extremely interesting and substantive. And as you mentioned, I'd like to welcome now Matt Spellbuck-Sharp. He is the head of sustainability at Ericsson. There, he leads the group responsible for circular economy for environmental performance, climate action, and sustainability impacts and benefits from ICT and from IoT. Welcome, Matt.
Thank you, Muriel. It's great to be here, and thank you for inviting me. So I will talk a little bit about what we are doing at Ericsson, and also together with our customers, as you heard. Earlier, we are working very close to our customers as they, if you look on the life cycle perspective of the impact of our company, the majority of the impact comes from the use of our products or in the networks such as Verizon's and others. And we have been very interested, and as a very engineering heavy and techy company, we base everything we do on facts. So we have done life cycle assessments and collected data from the whole industry for many years. I mean, 30 years when it comes to life cycle assessment and data for almost 20 years. So the ITU standards from International Telecom Union and the International Energy Agency data is to a large degree based on Ericsson research together with some of our customers. So we collect all of this data to be able to see where the trend is, and we see a great concern. And every time that we have launched a technology in the past, we have built a network on top of the other network, and that is why we have developed a model that we call breaking the energy curve. So already from the start of the standardization of 5G, we focused a lot of energy performance. So definitely 5G is the most energy efficient standard ever. So turning off 3G and 2G is one very good way of saving energy, and moving as much of the traffic as possible over to 5G makes it much more energy efficient to do that. And as I said, in the past, we added the network to the existing network. And that, of course, when you add something to something that's existing, that's also what Muriel talked about, then, of course, energy consumption will go up. But with 5G and with the new products that are launched, we can, in fact, manage several standards in the same equipment, and we can take something away before moving into 5G. And from that perspective, I think it is very interesting to see that we can build 5G without increasing energy consumption, and from that it will be possible to in fact not increase energy consumption or climate impact. And the other part, as you have heard, Verizon and a lot of the customers are taking commitments to move to renewable energy. So the ICT sector is in fact the biggest buyer. We are using around 4% of the electricity of the world, 3 to 4% of the electricity, but over 40% of all power purchase agreements on new renewable energy comes from the ICT sector. So as we heard earlier, Verizon is one of the biggest buyer, and the same is for the big data center companies. They are also, I mean, Amazon is, I think, is the biggest buyer of renewable energy in the world. So all of the industry is very, very proactive in moving to renewable energy, and also pushing new renewable energy through power purchase agreements like the green bond that Verizon did. So I think that is very commendable. So when we look at this, the increase of renewable is going pretty fast in our sector, and in fact Europe is the leading area. In US, 10% of the energy used by our sector is renewable, and that is much higher than the average. And in Europe, it's 61% of the energy used by the ICT sector is renewable. So very, very high degree of renewable. Also interesting facts are that between 2018 and 2020, when we have built 5G, we have rolled out all of these data centers, the energy consumption in US increased 2%, and the energy consumption in Europe increased 3%. The big difference here is China, where the energy consumption has increased 25%. So I think in these 3 years. So I think in China there is a big difference, and there they also don't have renewable energy. So there is differences in the different parts of the world, but I think from a general perspective, we are really taking the responsibility, and as an industry and the industry association are driving the the race to zero, and we are the biggest industry when it comes to commitments on net zero as such. So net zero commitment is across the whole value chain, and I think Ericsson announced as today our net zero commitment to be net zero in the complete value chain and by 2040. So 10 years ahead of what the Paris Agreement and 1.5 degree trajectories are needed. So going back then a little bit to what we're doing in technology. And there is this balance between proprietary chipset and openness and virtualization. And we will see that a lot of things will be virtual. At the same time, certain parts are much better when they are on the dedicated chipset. I think neither of us would like to have a gaming machine without a processor for the display and for a graphic processor in there, and the same with the mobile phone or other things. So for dedicated solutions, you need to have dedicated chipsets if you want to make them energy efficient, and then you should virtualize everything that is more generic, and then you can scale that. So that balance is extremely important if we want to continue to drive down energy consumption. Then I think the generic network, like the mobile network and the technology, driving digitalization in other sectors are extremely important also for the whole society's transition. We will never be able to increase the amount of renewable energy in the grids if we don't make the grids much smarter and much more agile with edge compute to control power and frequency in the grid, and also balancing energy over longer period of time. So I think 5G and the technology that we're driving are extremely important for society, for electrification of transports, for autonomous vehicles, for the grids, for smart buildings. And according to Ericsson research, as much as 15% of the carbon emissions globally can be reduced through the use of existing solutions from the ICT sector. And that enablement is hugely important. And if you compare that with the 1.5% of the carbon emissions coming from the ICT sector today, and that's 1.5% has been flat since 2010. So we are not, as a sector, growing our carbon footprint compared with other sectors. We are staying flat as a sector. And this has happened while building 4G, while increasing Google and Facebook and all the data centers and so on. So I think that the efficiency of both the software and the hardware in our technology has in fact absorbed the growth so far. And I think that we shouldn't be complacent on not doing anything. I agree, we need better tools, we need better software, we need better hardware, and we need to evolve. But I don't think we should be too worried either on that the ICT sector will be the biggest emitter in the forward, but rather a solution sector than a problem sector as such, as both driving renewable energy and being able to enable other sectors in their decarbonization journeys. So I think that all of these things are hugely important to remember when we take this discussion and take the questions from all of you. And I really encourage you to go in and ask us questions, because I think the dialogue is much better than me talking endlessly. So handing back to Muriel and looking forward to some good discussion and questions here.
Thank you very much, Mats. That was very important. That was very, very interesting. I'll just make a small correction. You said that the dedicated chips are more energy efficient. That's because when you use old algorithms, that is the case. If you look at our chip, it's actually more energy efficient than the ones you're using now. So check it out. But with that, I thank you. This was really fantastic overview from all of you, and the right amount of overlap as well as a difference in perspective, so richness in perspective. And I wanted to actually go directly already to some of the questions from the audience, because I prefer having as much time as possible from the questions from the audience. And I want to pick one in particular, which actually overlaps with something I wanted to ask, but is asked better than I was going to ask it. So there's one that says, you mentioned that energy is spread across storage, compute, and communications. What is the typical breakdown? And is there one source that dominates? And I'd like to open that to both our panelists, but I think particularly maybe to Heidi, since this is more of an operational question.
Yeah, as I said, it's amazing. Really, the devices take a tremendous amount of energy. I don't know what the quantitative percentages are, but I do know that along the spectrum, we actually get more and more efficient as we get to the core. But the transmission of data takes a tremendous amount of energy. And so, one of the things that we've done too is to move mobile compute to the edge, which allows us, or to cache at the edge even before we did mobile compute, so that rather than sending video, for example, which I think it's an hour of video takes like 55 grams of carbon emissions, it's very, very greedy, is we, rather than sending it over millions and millions of times as each individual user requests that video, we send it once to the edge and cache it there, and then use those assets out at the edge, which, Muriel, you talked about, are becoming denser because of us using those higher spectrum bands, which means that we get these lightning fast speeds and really high capacity, but we don't get the coverage that we had at the lower bands in 4G and 3G. But because we can do compute at the edge and keep a lot of that information, we're not traversing back and forth all the way back to the core, which is allowing us to be more energy efficient. Primarily for the reason that you talked about, Muriel, is because you're getting your customer on and off of that network much faster. And having a higher quality of service. Of course, when we get to a 5G core, and then we can do network slicing and actually do quality of service per user, then that will increase that efficiency that much more. So,
as I said, we have done quite a lot of research on these topics, and it's absolutely true what Heidi is saying, especially for the fixed equipment that you have in your home when it comes to the Wi-Fi's and the modems. When it comes to the mobile devices, as they have been battery powered, they are much more energy efficient in the user phase. So their biggest impact is in fact in their manufacturing phase. Almost 90% of the impact comes from the manufacturing of the display and the chipset and so on. So prolonging the life of your smartphone or your tablet is really the best climate action you can do if you want to be more sustainable as a person. And then if you look on the network in itself, I think around 15% of the energy is consumed by the core and the data centers, and 75% by the mobile parts of the network when we talk about the mobile network as such. So then it is the radio access network that is the most energy consuming part, and that's why we work so close with Heidi and others to put on sleep modes and making that much more agile on so zero power at zero load, and then transmit a lot of data in a very short period of time and then go back to sleep. So I think we have done a lot of cooperation on how to use AI and machine learning to understand when the network needs to be very awake, and then when you can put some of it to sleep. So when you have a lot of frequency band, you can use one or two of the frequency bands and to keep the network up, and then you can turn off the other equipment. So making it much more agile than it was. It was always on, and it should be always ready. So I think there is a big difference between being always on and like every light in the house on all the time, or turning on the light with something that when a movement sensor more or less, so it only turns on when you need it in a way. So that is what we are aiming for when we work together on making the network more flexible in a way towards the load.
And we actually have that working in our networks today, but we're getting better and better at it, right? And that's improving that system, and then also looking at even if it doesn't turn it off, when can it power it back, right? Yeah. So where we may not need as much coverage, and we can actually pull the coverage in, and so not have as much power coming. So it's not just zeros and ones.
Thank you. So actually, that's a perfect segue for another question, which is the relative importance of hardware solutions versus software solutions. Because I think what you just mentioned with respect to turning on and off is a perfect exemplar of this, hardware meets software solution. So I'd love to hear your thoughts. And since we started with Heidi last time, maybe Matt, I'll start with you.
Yeah, that is in fact a very good question. So I said that we are working very hard with the solutions that we are providing in Ericsson. In the past, it has been the power amplifier part and the hardware that has been the majority. As the equipment becomes smarter and smarter, the digital parts importance increases. But also in 5G right now, there is such a rapid development of the technology. So I think the energy savings only from one generation to the next of chipset is like 30%. So it's a massive energy saving, and that is hardware based. And then on top of that, we can use the different sleep modes. So there are sleep modes on sort of called micro sleep that you can do on the millisecond level to turn on and off the equipment when you have data to transmit or not. And then there are sleep modes that are more long term, so you can put it into longer sleeps up to sort of deep sleep when we more or less go down really deep, not turning it off, but going down really deep in sleep on the radios. And then the AI and machine learning on understanding the complexity and the traffic situation and to wake up in time from the deep sleep and so on will be more and more important going forward. So I think until now, hardware has been extremely important and the development of hardware has been extremely important. But as we move on now, I think the software part will be growing in importance.
Yeah, I agree. And not just from an energy perspective, but from an ease of deployment perspective. So, we absolutely are on this journey to get to just COTS hardware that we can then take secret sauce software from Ericsson or some of their competitors, because it makes it easier for us. Like right now, every single cell site in the network is being touched in order to add mid-band or C-band, you may have heard of it called, that we recently won in an auction. And so it's very labor intensive. And that drives energy. One, there's the manufacture of the hardware, but then there's also getting trucks out to each of those sites, right? And doing the construction, which increases energy just from the power that's needed to do the construction. And ultimately, the goal is to have where we would just have off-the-shelf hardware, almost off the shelf, and be able to use software to make those tech upgrades. And then that also would help with energy consumption, as I said, but also speed of development, which then would allow us to get to the more efficient technology faster. As I said, there's some barriers to getting there today that would be greatly reduced from the time frame perspective and allow us to tap into that efficiency much sooner. And then it also allows us, as Matt said, then you get into when it's really software based, then you can use machine learning and AI to be able to only use those assets when you really need them for the purpose that you need them, and you're not providing capacity when it isn't required by the end user. So utilizing energy to do that.
So that's very good, and it actually ties into one of the questions we also have around the current use of machine learning in for resource management and energy optimization.
Yeah, so I can say what we do from an operator's perspective, and then Matt, I know you from an OEM perspective are doing an awful lot in that space as well. So there's a few things. We've been using AI for a while and data analytics to help us put sites where they will be most useful. And so obviously the less sites that we have, the less energy that gets drawn, because we don't require power to sites that aren't really contributing to the overall network experience, and we're not doing cooling with them as well. And so we've been able to be more efficient in the placing of any new builds that we do. So from that perspective, we've been doing that for 4 years now, has really helped decrease our CapEx, but then also decrease the OpEx in order to run those sites, which ultimately helps us be more efficient. We've already talked about some of the sleep mode that we're doing. I had mentioned earlier that we are also building algorithms to look at where do we see elements in our network that have abnormal or anomalous energy consumption. And so why is that the site, the data center, the card, whatever it is not operating at the efficiency that we would expect out of it? It also allows us to see what network elements are contributing most to the overall load, so that then we can say, okay, how do we go target that in order to be able to upgrade it and make sure that we get that out of our network as quickly as possible. We use it too, even with like the shutdown of CDMA. We have a lot of large corporate customers that have 3G IoT embedded in cars, in pipelines, in agricultural equipment that they did not want to have to upgrade. And we were able to show internally what the power consumption savings would be and how it would contribute to our goal to become more efficient, and how that then plays off of the revenue and how we can help with some of that migration to new devices. So.
Thank you. Mats, what is your view on this?
Yeah, we use machine learning and AI on several different levels. So within sort of the radio equipment, the antenna and the radio equipment, there is AI and machine learning algorithms on how to improve energy and the traffic situation for that specific radio, and then on the site level to turn on and off frequency bands in a smart way, depending on traffic and understanding when, if you at the train station, when do the traffic come and so on, and over the week. So learning patterns to be more aggressive on or more intelligent on using the sleep modes of the different frequency bands and so on. And then we do the same on network level, on clusters and bigger levels, where we turn on and off not only the active equipment, because we shouldn't forget about, if you have a site, there is also quite a lot of rectifiers and in some cases air conditioning and other equipment that is also using quite a lot of energy that can be turned on and off. So we have sort of energy intelligent operations. So on an operational level, on a network level, we can do that. And then another interesting part is that we realize that there is currently in the mobile sector a race towards higher and higher output power on the radios. So there is a request from many of our customers to increase the output power to sort of have better range or better performance in the network to get good rankings and so on. But we realized recently that they're driving this output power also causes a lot of interference. So we used machine learning and AI to sort of tune down the output power of equipment, and we improved the performance in the network by turning down the output power to reduce the amount of interference between different sites. And then we did calculations on how much we should do that. So both saving the energy, improving the traffic performance, and reducing output power. So that was a very interesting use case for AI and machine learning to sort of map that across the network and learn how to do it based on the topography.
The other thing we're able to do with the AI that Matt's just talked about is if we have an event like a huge football game or something like that, then we can direct the resources towards where we know the traffic will be. Well, we don't do it. The network does it itself, right? And it knows that it's seeing a large spike in traffic and will put the capacity there. That's allowed us to build less sites because we're not engineering for the maximum amount of usage. We're able to beg, borrow, and steal at the right times from areas that are using it less and point it into areas that need it in that time and space.
Thank you. Thank you very much. Actually, that's a nice segue into two questions, which I'm going to merge together because I think that they're sufficiently germane. And this goes back to the issue of the manufacturing and the carbon footprint of the manufacturing itself. And whether a more modular approach might be helpful there. And connected to that is the issue of the specialization of the devices or not, particularly given that some of the discussion yesterday pointed to, and Matthew had made that point, that specialization can be more energy efficient. Well, of course, it depends on the algorithm. And just to be clear, the reason our algorithm is better is not because it's trying to do our chip is better. It's not because it's trying to do old algorithms. Of course, whenever you do something that's existing, specializing is better. It's just because the new algorithm happens to be universal and is just that much more efficient than the old algorithms. But in general, again, generalities is very, very difficult, but is generally wrong. But what is the trade-off between specialization, not specialization? What are the benefits of modularity? You both spoke about the challenges of going back and removing, say, 3G CDMA systems, and I'd like to really get your perspectives from both of you, and maybe this time starting with you, Mats.
Sure. So, as I said earlier, if you look on the life cycle assessment of the Ericsson activities, over 80% of the impact comes from the user phase, and that's why we have focused so much on that. But 13% comes from the manufacturing. And this is, of course, in the current situation with the global average and a lot of fossil fuel used to power the electricity of the networks globally. So to the degree that we, in fact, have a higher material flow, even the material and metals that are shipped in the energy cycle is bigger than the one that we ship to the market. So it's pretty staggering numbers that is used by the energy as long as we are using fossil fuels right now. Then going back to the question on the balance, as I said, the Ericsson Silicon has helped us to reduce the footprint in the manufacturing phase and integrate much more in the radio side. At the same time as we are working both with Open RAN and providing a lot of input to that and virtual RAN solutions with more generic equipment. So here I think in the future, when there is very generic and a lot of data going to the edge, there will be a lot of generic computing equipment that can be very flexible. Still, I think the beamforming parts and the radio signaling parts will be best suited to be carried on dedicated silicon in a similar way like you have graphic processors to do the graphics in a gaming machine or a computer. So that is how we believe that it will evolve going forward. When it comes to modularization, yes, we are doing that, but we are not doing it on a modular way. So we have like Lego putting it together. It's more that we have chipsets that we can sort of put together and scale. So the design is modular rather than the products are modular, because there's so much integration between the different parts and so much that needs to happen in high frequency when we are talking about the frequency bands and so on. So doing the connectors on all of these would complicate it too much. So, but it is modular already from a design and conceptual perspective inside the products, but it's not modular, so you can put it together on as Legos yet, and we haven't found a good way to do that. We have been looking at it, so I think that is where we are on the journey towards both making it more open as well as making it modular in a way.
Thank you.
Yeah, from an operational standpoint, getting to more standardization, modularization, if that's a word, is good for us as well. Like anything that we can do to reduce spares that we have to hold, because of course, again, then that is more manufacturing, it's more warehousing, it's more transportation, it's more, times going out to the sites is good for us for a lot of reasons, but certainly from an energy perspective as well. And then, as I've said, the more that we can do from software upgrades opposed to doing hardware upgrades is beneficial as well. And then, one of the things that Ericsson has been great working with us as we go to C-band is making the radios integrated, as Matt said, so that we have everything within a single sheath. And then it looks as much like our 4G radios as possible so that we can go out and do like for like swaps and not have to do any increases in energy, cooling, et cetera. But as Matt said, the 5G equipment is actually, some studies have shown, up to 90% more efficient per unit of usage, right? So we're able to handle tons more traffic without having any additional energy consumption. So the more we can get to software, but one of the things we've learned in our virtualization journey is that not everything should be virtualized, and I think that's what you were saying, Mats, right? Is I think when we all fell in love with virtualization, it was virtualized at any cost, and then we realized that really there were times where the cost to the network, either for the assets, spectrum assets that we have, or power, et cetera, didn't make sense to virtualize. And so I think that's where we're really working with Ericsson and others right now, is to say, okay, where does it make sense to have that modularization? And where does it make sense to virtualize and go to software rather than have hardware that is unique?
Thank you. So actually, in terms also of modularization and to what extent equipment can be, can be reused or repurposed. There's an interesting question on the chat about the scaling of computation. Oh, sorry. Go ahead, Mats. Yes.
No, I just lost the connection. So.
Oh, no problem. Ironic. There's an interesting question on the chat regarding the scaling of computing with higher bandwidth. So we've just been talking about the issue of modularity, but also, as you were saying, of how much is baked into the ASICs and how much is done is done virtually. And I think this leads very well into the question of the scaling of computation with bandwidth, particularly as bandwidth increases with increasing generations. And I'd like to direct this one first to Heidi, since that's a little bit more in her wheelhouse, but obviously in both of yours.
Right. So trying to decide how to start this. So I guess really as we more efficiently utilize spectrum and all the backhaul that we use for the equipment and then the computing, right? So as the technology has improved, we've been able to become more efficient in how we utilize every segment of that end-to-end circuit that provides information. And so again, it really is about being able to use bandwidth to be able to provide more capacity and greater speeds, which makes everything more efficient because you're getting folks on and off the network more quickly. They're having a better experience. We're able to put more traffic over a single pipe, if you will, although it be a virtual pipe at this point. So as we continue to get better spectrum and that's able to handle more, and then fiber continues to become more and more efficient, which is why it's so important for us to get off of copper onto fiber optics, that then again through the physical conduit and the fibers don't need to be swapped out. We're just able to become more efficient on the existing infrastructure, then the more efficient we become. I don't know if that answered the question or not.
I think you definitely touched on some of the core aspects of the question, but as you said, where does one start? This is a very wide-ranging question. So I'm going to direct it to Mats. That way he can.
Yeah, it is very wide, the bandwidth now. So I mean, we are with the higher frequency bands. There is a big. I mean, we can have better data capacity with the bandwidth, and I think that is available. And I think what we do with 5G is also the reason why we need sort of the ASICs is really about directing the signals in one direction. Is another thing where we are much more energy efficient and efficient now with the MIMO radios. So with the higher frequency, we can also make smaller antennas, but make them into arrays of antennas, and by that make a directional signal. So instead of sending signals in 360 degrees and where sort of the attenuation is much bigger, focus it more. It's not like a laser beam, it's more like a cone of radio signals that we keep sort of directing it at where we want to send it, but still it is much more energy efficient and also provides better sort of range, because we can direct it in to where it's needed. So from that perspective, we can be much more energy efficient in the transmission and transmit a lot of data in a shorter period of time. So I think that goes back to the sleep mode. Sorry, Heidi.
I think you just made an excellent point there. That beamforming will continue to evolve as well and become more and more efficient, right? Not only within the radio, but as we move over to 5G core as well. So just for anybody who doesn't know, we have 5G radios today, but they are operating on our 4G core. Yeah. So we have not moved to full end-to-end yet.
If I may just explain for some of our some of our audience what beamforming is. So we're talking here about in radio channels, the antennas have basically things that in the electromagnetic patterns that look like bunny ears. So it's around, I don't know how else to describe it. I'm sure you have better ways, but just for some of our audience, because that might be a little bit specialized. But that's what
I think the easiest way to understand
it's changing the bunny ears, and overlapping the bunny ears.
Exactly. So normally you have sort of a normal antenna that you have is sending sort of 360 degrees, and in the traditional antennas from mobile networks, you had sort of 1/3 of the angle, and then it was sort of narrow, so that was sort of directing the signals like a torchlight sort of. And what we are now doing is sort of focusing this torchlight much better by controlling a lot of small antennas that we can sort of frequency control, and by that then direct the signals like we do with the torchlight. So I think that is what we're doing right now, and where we can be much more efficient in reaching the receiver of that signal. So we can do that for different places at more or less the same time. So that is why this requires enormous amounts of computational power and a very specific type of computations that you do over and over and over again. And that's why ASICs are relevant for that part, when you do the same thing over and over again, and a very specialized extreme need of computing power. So that is why sort of the Ericsson silicon is so important for us in becoming more integrated and more energy efficient. So in fact, we have reduced the size of the product between generation 2 and generation 3 of 5G phones with 45%. So it's enormous integration that we are doing, and at the same time reducing the energy consumption with 30%. So in one generation of chipsets and making it much more efficient. So a radio that when the first 5G radios came, they were 60, 70 kilos. Now they're down to 20 kilos. And they can still have higher output power. So the development over just a couple of years has been enormous in this area.
Thank you. So I was just trying to be a little bit conscious of the fact that we were getting a little jargony, and
Sorry, yeah.
Oh, that's
no,
great.
I tend to do that all the time, so I'm particularly conscious of it. So actually, this is also a good segue to another question, and this time I'll start by directing it to Mats, particularly as a manufacturer, which is around Moore's law. So I'm paraphrasing the question and adding a little bit of my own interpretation. But there's been a lot of discussion as to is Moore's law really going to hold up for much longer? And the question here is what other technologies are being explored right now to meet increasing computing and requirements and also maintaining energy efficiency.
To paraphrase an emperor, I think the rumor of my death is greatly exaggerated. I think Moore's law is still working. Of course, we see that it's slowing down a little bit, but still we are happening. But I think it's not only Moore's law on the hardware side; it is also the software and how the algorithms, as you talked about, Muriel, and how the algorithms evolve and how much more efficient we are in by new ways of radio technologies. So it's not only the hardware, it's as much, I mean, the difference between 4G and 5G and what we have learned on how to build and drive radio interfaces and do different standards. So it's not only the hardware part of Moore's law, it's as much, I think, the reason why 5G is at least 10 times as energy efficient and efficient in as 4G is not only because of the hardware, it's also thanks to the software and the way that we are building it in a new way and reinventing ourselves in so many ways. And we have already started with standardization work for 6G in US and in Europe and in other places. So we are already talking about the next step on that. And I think it is amazing what we have managed to do by creating this global standard for mobile communication. Because the prices of the chipsets and everything, thanks to the globalization and the way that we have been driving devices, is enormous. And I think it has changed so many things. I mean, the way that we, the smartphone and the way that we use cameras or don't use cameras anymore, but use our phone for that, and the way that we sort of pay with, I think so many changes. I remember when I was young, and I'm very old, as you can see from the screen, when you sort of called the place instead of calling a person. Then you answered your phone with sort of who you were. Now you answer where you are instead. So it's sort of, it changes the whole social life, the technology that this is about. So amazing to see the next step now when 5G goes into the industries and our lives in different ways, the whole society.
Yeah, I tell everybody I started when wireless started, so I've been around a long time as well. And I had a bag phone that was about this big and was very heavy, and I was lucky if I could make a voice call on it. And now, I can rule the world with this. Sometimes I'm not even looking at my computer. I'm, purchasing things on the phone. I'm checking where my daughter is. I'm FaceTiming with her. It's just really amazing what we can do on this small device. Like you said, I never use my camera anymore. I don't have a calculator anymore. We don't have a paper calendar. Everything is on the phone. And I would have never imagined that 30 years ago. And so I always chuckle a little bit when there are questions such as this, because I think, there's been so many times in my career that we thought, well, we've reached the end of the rainbow here on this particular capability. And then we always surprise ourselves and we're able to push through that wall and then increase capacity, increase speed, decrease latency, increase energy efficiency. So I just don't believe that we've reached the end of the ability here on Moore's law either. So.
Thank you very much. And actually, just as a comment, Moore's law is often misconstrued as being all about the hardware. But if you look at the original statements from Moore, were actually about algorithmic improvements. So the prediction included that there would be algorithmic improvements, and goes back to our previous discussion, and that has been a little bit forgotten. I think quite forgotten. But his original view was that it had that algorithmic improvements would be a large component of those gains. With this, we're getting into our last 5 minutes. We haven't. This is really an MIT sustainability event. So I'd like to close with a question, giving you some time for remarks, and also a question about what can be the opportunity for interactions between academia and industry in this problem of sustainability. And since we started with Heidi, I'd like to start now with Mats for closing.
Yes, I think one of the key things that we can do together are in developing standardized interfaces for data. I think one of the key areas going forward will be that when we see the Internet of Things and the great improvements in society that are possible, as I talked about smart grids and transportation and so on, all of these are developed in silos as it is right now. Mm-hmm. And I think when we can sort of connect these across, when the smart grid is truly understanding the transport system and the smart buildings and the cities, when we get that is when it will take off. And I see right now that there is sort of a tendency by big companies trying to lock in everybody into their ecosystem in a way, which is, that is how some of the most valuable companies have managed to become most valuable. So I think it's an understandable model. But I think if we could generate more of a generic platform across industries in a similar way like the mobile system, even though it is sort of IPR and so on, it's protected, but still it is. You don't know if you call on the Nokia network or an Ericsson network. It works everywhere. And I think that type of standard also for APIs and for data going forward to utilize 5G fully. I think if we could work together on creating that as fast as possible, then I think that would be a door opener in a similar way. Because I remember when I started in the mobile business, I could not use the same phone in US as in Sweden. It was mobile phone telephony was local. And then we started roaming, and then the whole thing took off in a totally different way, I think. So if we could create those standards in a way, that would be my biggest ask. And then, of course, keeping it fact-based and not taking too easy conclusions is, of course, also extremely important. And there, I think science and we work very close to different scientific institutes when it comes to the research and life cycle assessments and so on. So I think there we are happy to continue that cooperation.
Thank you, Matt. Heidi.
Yeah,
how do you guys use research, advancing the technology? Where do you use it?
Yeah, so we do partner with quite a few, universities, and do look to academia to input. And then I know they also do with our key vendors that then we benefit from. But I would build on what Matt said is, yes, we love to have Verizon be the best and most reliable and have secret sauce. But I do think driving towards more standardization that is fact-based. There's a lot of, I actually am a biologist by education, not an engineer, but I use the scientific method all the time and say, all right, we have these hypotheses, but now we've got to go do the research or have MIT do the research for us and make sure that our hypothesis is true. And as a corporation, I think we're very quick to jump at an idea without having that fact base behind it. And academia can be extremely useful to us, not just in the compute that we use, but maybe in some of the use cases as well, right? Like a lot of the efficiency that we have is not just within our own network, but also, as we said, helping to decrease transportation, being able to help with agriculture and less water by using IoT sensors and drones, et cetera. And I think especially, students and doing research, that there are things that we won't dream of in a corporate scenario that would be very useful, and that we ought to think together about how do we create that ecosystem to continue to help with the communication, but also do it in the most efficient way possible.
Thank you both. Matt, Heidi, it has been a pleasure. Thanks to
Same.
all of our audience and their great questions. There will be a 15-minute break now, and I encourage you all to join again at 11:30 if you can for the next session. Thank you.
Thank you.
Okay, well, welcome to the next session of our workshop. I am Dave Peralt. I'm a faculty member in electrical engineering and computer science at MIT, and my own personal work is on power electronics, energy conversion, and their application to advance all kinds of systems, and especially improving the energy efficiency of systems. So today's workshop is of great interest to me. And so I'm very happy to be here and to see all of the interesting work we're seeing today. Next slide, please. So just to show you where we are in the workshop, in the Climate Impacts of Computing and Communications workshop, this session is session 5, and it's really focusing on energy efficient systems. Next slide, please. So if we think about things at a systems level, we saw earlier today, and I think our earlier host Muriel Medard mentioned the magic of computing and communications, and really technology has advanced to the point where computing systems and communication systems and what we do with them are almost indistinguishable from magic. And how have we gotten here? In part, we've done that by taking really tremendously challenging problems and breaking them down into smaller ones. And so we work on designing subsystems that can address parts of these problems, and then stacking them both laterally and hierarchically with very clean interfaces in order to break the problems down. And then we send, sort of relentless innovation and optimizations of these subsystems with all of the other subsystems around it abstracted. And in addition, as we advance technology, we often build new systems where we construct them on top of or within the framework of earlier ones and keep upgrading. And that's been a very powerful tool, which has been allowed us to reach where we are today. At the same time, this method of operation necessarily results in a lot of siloing, of really where we can focus on highly optimized subsystems, but that may not be the best use overall in terms of the use of energy for the whole system. So each part may be optimized for what it's doing, but without a view of the whole system, we often sort of have something that's locally optimum, but globally far from optimum. And moreover, a lot of challenges at the subsystem level are often addressed or papered over by essentially throwing energy at the problem. There's some more energy you throw at the problem, you can kind of address some of the real major challenges. And the problem is that this usage of energy often compounds among the systems. So the overall system draws far more energy and has far more environmental impact than really required. So it seems that taking a systems perspective and rethinking the subsystems and their interfaces is really an essential step to dramatically improving sort of these computing and communication systems as a whole and mitigating their climate impacts. It is a very challenging thing to do, as I've seen from personal experience, bringing in kind of new paradigms and sort of breaking out of this subsystem mold in order to achieve a global benefit. But when you can do it, it really can have a large impact. And I think this is also an area where we can marry the strengths of industry and academia to really achieve these dramatic improvements that we're seeking. So I am really excited today in this session to hear the thoughts of our speaker and the thoughts and questions of our audience. And so I'd like to introduce him. Sam Nafziger is an AMD Senior Vice President, Corporate Fellow, and Product Technology Architect. He works across the company to optimize product technology choices and their deployment with a continued focus on driving best practices to maximize product competitiveness, efficiency, and cost. So he's really looking at the level that can really bring a lot of these benefits. So I'm really excited to hear what you have to say about reducing the climate impacts of computing across all scales. So Sam, please go ahead.
Great, thank you, David. Well, I'm super excited to be here, and it's a topic near and dear to my heart, my focus. And I love talking about our technology and how it improves efficiency and environmental impacts. So I'll jump in here talking about the broad view of architecting for efficiency. Like David said, it's a system level problem. So the landscape, to start with, is that a big contributor to compute power consumption is the accelerated computing, and that involves a number of different components, different markets, high performance computing, AI training, as well as many more satellite market areas that share the intellectual property components and the silicon devices to support those markets. So these are growing very rapidly, and I'll show you some data along that line. And that results in a lot of energy consumption, especially combined with the fact that the energy use of these is increasing due to a number of technology factors. So we, at AMD, are focusing on win-win solutions that improve the efficiency of these products while also benefiting the environment and delivering the compute performance that the market demands. And market demands have been escalating even more rapidly than in years past. And one of the great examples, it's easy to track, is the performance of the world's fastest supercomputers. And as you all are well aware, these installations are used to solve many pressing real-world problems that affect humanity, the future of the planet. We deploy into these giant installations that do protein folding simulations, model the climate, support exploration for new energy sources, and many other different pressing and high-value problem sets. These systems they've been doubling their performance every 1.2 years or so. If you just run that trend line through, that's using a metric of a well-known metric in the industry, LinPat gigaflops, double precision floating point, and this growth rate significantly outstrips Moore's law, which is approximately 2 years doubling. And so there's a lot going on in these installations to drive performance beyond just the silicon CPU or GPU level, but delivering performance at the system level, which underscores the value of optimizing that entire system. Another great example is different but shares common components, the gaming market. And gaming is highly compute intensive to render these images in buttery smooth, high frame per second quality while providing high resolution features like ray traced imaging and lighting that greatly improves the realism of the experience. Our world is paying a lot for these gaming systems, and their usage has been growing dramatically worldwide, with esports rivaling many physical sports for investment, advertising dollars, and interest levels and viewership. So the underlying performance that supports these improvements in the gaming experience can be boiled down roughly to floating point operations per second. These are lower precision floating point operations typically than for supercomputers, but it's been growing at a similar exponential rate. And there is no indication that these growth rates are going to abate, which means in the next few years, we're going to have to find ways to deliver a tripling of the floating point performance of today's GPUs to meet the market demand. Obviously, we do not want to be tripling the power consumption of these processors, so innovation is going to be required. Another great market to talk about as an energy consumer is machine learning. And there are basically two classes of machine learning application. One is on the inference side, where the smartphone or laptop uses a pre-trained network to accomplish its function of maybe language translation or image recognition or background blur. Other effects. Training those networks is what takes most of the energy. It takes a huge amount of energy, and these networks contain parameters, which are the things that get trained to do their impressive recognition functions. And to reach human levels of capability in these different applications requires a lot of parameters. And we're all beneficiaries of the higher accuracy of these recommendation systems or natural language processing systems. But the parameters are growing at an astonishing rate. Forget 2 years or 1.2 years. We're talking 2.3 months for a doubling of these parameters. And that means we have to invest the compute time to get the correct value on each one of those parameters for the system to deliver its accurate function. So these capabilities are consuming a very large amount of energy. And in the face of all that growth and demand, we are, of course, dealing with the Moore's law slowdown that has been much discussed. And so we all know that the technology nodes aren't what they used to be. The introduction rates are fewer and far between, and they are delivering less, even though they come later. Combined with that is the increasing cost of these process nodes and the increasing die size of our processing elements. Those you might not think are directly related to energy, but as the costs go up for the most advanced node, that means we are motivated economically to use less advanced nodes as much as possible. They are, of course, less energy efficient than the most advanced node. And the large die size problem means we have to start splitting up our designs into multiple smaller chips, which of course requires communication between them, less efficient than a single piece of silicon. So these are all some of the factors contributing to the fact that the, just taking an example here, the absolute power of the top supercomputers is going up significantly. And that's to deliver that, doubling every 1.2 years. And this is just a sampling, many other examples of how power consumption is increasing in the compute space. So we have a lot of challenges with the energy dimension of our compute demands worldwide. And this has been codified nicely by the Semiconductor Research Council with a report that they put out in the Decadal Plan a year or two ago. And it showed the growth in compute demand as shown in this green curve as boiled down to the energy consumption in joules per year. And it's on an exponential growth path, which given what I just showed earlier, not surprising. And we can see that in 2030 or so, we're getting to very sizable fractions of worldwide energy consumption, and that's problematic. We don't want to be increasing energy consumption worldwide for a host of environmental reasons, and if compute is consuming a very large fraction of it, then we have a significant worldwide issue. So we need new approaches to meeting this compute demand, because when we look back at the efficiency of general purpose processors as plotted here from 1971 up until 2020, a very interesting observation can be made that as we have increased the performance of these processors, that's the y-axis, the instructions per second. So everybody wants higher performance processors. They do their computations faster, the quicker response times, we can do more complex tasks. But the x-axis here is the bits switched to deliver that processing performance. And this is a log-log scale. You can just see by the slope of the curve, it takes a lot more bits to switch to deliver a small increment of performance than the actual performance improvement. So we're really at about a 2/3 log improvement rate here, which is, if we're going to be growing the compute demand as exponentially as I just showed, we need a much more aggressive trend on the improvement in compute efficiency. And so that means we're going to need new approaches, and a clear opportunity here is with more special purpose domain specific accelerators. And shown conceptually, the value proposition of these accelerators is that they do a smaller number of things much better. A general purpose CPU, if you just look here, applications and the performance per watt, the general purpose CPU is great because it's ubiquitous, easy to program, and the application set it can use is very broad. GPUs have gotten quite a bit of traction in a number of markets outside of just gaming, because they do the highly parallel throughput computing and can deliver much better performance per watt on those sets of workloads. Now you try to get GPUs to do database processing, for instance, they're going to be very inefficient because their whole microarchitecture doesn't apply there well. And then in the the red here are more special purpose accelerators, and a great example there is some of the machine learning training and inference architectures that are proliferating. They are great at those specific tasks, but only at those tasks. So our application-specific accelerators is going to be absolutely essential to improve the performance per watt, meeting that compute demand. And in addition, in the face of those technology challenges I went through on the process technology, the silicon technology, we've got to get very good at doing chiplets, which is now becoming an industry term for disaggregating what would have been a very big single silicon chip and do multiple components and specializing those components for higher yield and efficiency, and then putting them together with low overhead interconnect. And this is moving to 3D, which I'll talk a bit more about later, which has great promise for not only improving raw performance, but the efficiency of each of those compute instructions. So modular design and application specific are going to be very critical elements to improving our performance per watt. And another area is on the algorithmic side. There's been a lot of research that's accelerated recently in the face of the machine learning, the importance of machine learning around making better use of the bits in our floating point operations. That's the way I would put it. So we've been using, or it seems like forever, my entire career, the IEEE floating point 64-bit and 32-bit formats. We have an exponent and then a mantissa for the fractional component. And these are the mainstay of high performance computing tasks. It's how we measure performance level in those supercomputers. And these formats, they're great, they are robust, but they are overkill for a lot of applications. So we're finding in the gaming space that we can make use of lower precision math and deliver an image that looks just as good with 16-bit computations as when we use 32-bit computations. And a lot of great research there. And of course, in machine learning, we are pushing down to much lower precisions, or we're moving bits around from the mantissa, like in this BrainFloat 16. It's 16 bits worth, but instead of a big mantissa, we drop a few bits there, put them on the exponent, we get greater range for those computations, which helps those algorithms converge faster. So we get higher performance with the same number of bits, which means it takes less energy to train those billions or trillions of parameters that I talked about earlier. So research in these math formats is a great area for collaboration, finding the right format for the right task. It's kind of another dimension to the accelerated computing thing I just mentioned. Algorithmically, we can accelerate certain workloads with lower or special precision math and get more done with less energy and less time. And plotted up here, just which I didn't talk to you, is the energy consumption. And the thing to note is, first of all, CPUs, they're very general purpose, critical to the industry, but they are not the most energy efficient when it comes to just pure math computation. You run those same 32-bit computations on a GPU, the energy drops by about a factor of 3. And then if you cut the precision in half, it drops even further, and 8-bit down again. So when we can craft our algorithms through software and the equations used, et cetera, to converge with lower precision math, we're much more efficient. So now I'll talk through some of the recent AMD product results, which provide higher efficiency, and make some comments as we go. So this is what we call our Instinct line, which goes into that high performance computing space and the machine learning space. And so these are the big iron computing elements, you might say. And we've been making significant generational improvements here on the left in the absolute performance. So peak teraflops per compute device, and we track these in mainly we would two different categories, although we have multiple precision supported. The FP64 here is the most important one for those supercomputer deployments. FP16 and its derivatives, most important for machine learning training. And you can see the gains in absolute performance here, pretty substantial generationally, especially when we're talking just 1 to 2 years between generations. So this is the sort of improvement that supports that compute demand I talked about earlier. Now you'll notice, your eyes may have been attracted to the power number down here at the bottom. You can see that the thermal design power for these GPU compute processors has been growing. And a number of reasons for that. One is we're doing a lot more computations in these devices, but the other is, as I mentioned, the technology nodes have been slowing down in their introduction and improvement rates. And in fact, these last 3 processors are all fabricated in TSMC's 7 nanometer silicon. So any performance per watt gains we get don't come from silicon improvements, they come from architectural and algorithmic gains, or through chiplet design approaches. And you do see substantial performance per watt gains here on the right. So FP64 in particular makes huge improvements. We go from 0.038 to 0.171. So, about a 4x improvement in the flops per watt with this MI250X processor, which is great. It means that exaflop supercomputer that we're deploying all of these into is going to be much more power efficient than the ones that had gone before, despite the fact that it's in absolute terms higher power, but it does far more watts than the power increase. Sorry, it does far more flops than the power increase. Now, you can look here on the right and say, well, what's wrong with the FP16 performance per watt? It didn't, it took a big leap here from MI60 to MI100, but not so much to MI250. And this points to the power of the architectural improvements that these designs can exploit. And what we had done in moving from MI60 to MI100 is implement dedicated matrix math pipelines in the design, which are optimized to do the general purpose matrix multiply functions that are most common in machine learning training algorithms. And when we organize our data path to do a whole bunch of floating point operations chained together in a matrix multiply fashion, we have a lot less data movement and a much more efficient floating point operation. Since we already made that move for MI100, and the technology didn't improve, it was more difficult to increase the performance per watt without that big architectural enhancement. So this shows both the power of architectural improvements and the need for continued innovation in that area. So I want to switch and cover a bit about EPYC server, CPU server processors, because CPU servers are still the largest energy consumers in the data center worldwide, and it's critical that we have a great performance per watt story and long-term plan in this space. So we're very, I have to say, at AMD, very proud of our EPYC servers, which have substantially higher performance per watt and have had that for many years relative to the competition. And you can see here how that boils down, and that in order to perform the same amount of work, in other words, a 10,000 integer score, so we have a certain amount of computation to accomplish, and you can do that computation on either one of these systems. On our competitor system, takes 17 servers to do that. We can get the same work done with just 12 servers, and that means we consume not only less power in the process of accomplishing that compute task, but we consume fewer resources to actually build and manufacture, and the energy that goes into producing the sheet metal and the silicon and everything else for these servers. So the higher performance of the servers and the lower power consumption combine to have significant environmental benefits. And it's an area that obviously we're going to continue to drive. And another aspect in the CPU server space that needs to be understood is the virtual machines. And the way The cloud works, of course, is basically the data center owners rent out the compute capability of these machines to whoever wants to rent them. And they are divided up into virtual machines, which run the tasks of the customers. And the fewer physical machines required to run these virtual machines, the more efficient the computer is going to be. So you can see here, once again, we're pleased with the results that we've been able to deliver, and that we can serve the same number of customers with a given amount of compute measured in virtual machines with significantly fewer sockets. And that means that it's lower operating cost, lower hardware acquisition cost, and lower energy footprint in the process. So higher performance and lower power per operation are big levers in the environmental improvement space. So I'll wrap up the product level view here with high-end gaming, because this is an important energy consumer worldwide, and another area that we've been focusing heavily. Like I said, it leverages a lot of components common to the compute space, that Instinct line. And I'm especially pleased with the results we've done, because once again here, these are the same 7-nanometer technology, but we've managed to, through architectural enhancements, drive up the performance per watt by 50% at least each generation, which is a difficult task to achieve, because it requires innovation at the architectural, at the silicon level, and at the software and algorithmic level to accomplish. One of the ways we accomplish that, just to give you an example of the kinds of innovations we need to do, is in leveraging very high density on-die fast SRAM memory to decouple ourselves from the DDR memory that serves the GPU and traditional implementations. That GDDR6 memory, it's very high bandwidth, special purpose for gaming, but it consumes a lot of energy per bit transferred. That's the 7 to 8 picojoules per bit, and that's a good measure of the energy efficiency. If instead we are accessing those bits from our on-die, what we termed infinity cache, it only takes 1.3 picojoules to get that same information. So clearly, if we can implement this cache and most of the time go to this infinity cache for our images and image and rendering information, we can generate much more bandwidth per watt, higher performance per watt, which is exactly what we've done. So these kind of architectural enhancements are great areas to collaborate with academia on, finding more energy efficient ways to deliver the same or better performance that we need to supply the world's demand. I'd be remiss if I didn't talk a little about 3D, which I think is one of the most exciting vectors of innovation in our field here. And instead of designing just planar silicon, we are exploring ways to stack multiple pieces of silicon on top of each other and get significant benefit from that. And we have just productized what we've called a V-cache design that stacks a very highly dense SRAM cache to supplement the existing cache on the baseline compute chiplet die, which is here. And that increases performance substantially by about 15%, which, if you're in this industry, you know that 15% performance is basically a generational performance gain, very hard to come by. And we have managed to do that with just stacking this additional die on top and connecting it up properly. Now, the better thing about this is it delivers that performance in a power neutral way. So we didn't have to add higher power CPUs. We didn't have to raise the frequency and voltage. We just put this cache on there, and kind of like with the infinity cache on the prior slide, we save energy by accessing this local high density SRAM instead of going out to main memory. And the other great thing about 3D that we talk about here is the fact that it's intrinsically energy efficient. because it reduces the distance that bits have to move to get to where the consumer is. So with 3D, and you can see the spaces here, so we've been doing chiplet designs for quite some time. We have multiple die on the package substrate. To communicate between each other, they have to go down to the package substrate on these long routes. These are thick copper wires. So if we'd put the additional SRAM down on the substrate, like where this IO die is, we would have to be transmitting those bits across this, this energy consuming interface. But instead, by stacking it on top, we have these tiny little through silicon vias that connect directly to where the data needs to go. So dramatically less energy, 3x reduction in energy per bit, and that's actually greater. That's relative to alternative 3D stacking. Against 2D, it's 10x or more, and the interconnect density is dramatic. And so the benefits of this are many. We can enhance the compute functionality without growing the power consumption. We can stack heterogeneous compute die, special purpose accelerators, to get their energy savings and have the data very local. So we are excited about the promise of 3D. Look forward to more ways of exploiting it. So I'll just spend a couple minutes on how we are turning all of those innovations and the challenges that we see into a goal to improve our efficiency by pretty dramatic amounts in the coming years. The context for this is just a synthesis of what I went through before. If we look at the volumes that are expected to ship in future years, based upon industry watchers, and with our knowledge of how much energy each of those compute nodes is likely to consume, we can plot out the energy use over time. And the biggest energy consumer today is, like I mentioned, the CPU data centers. Those are the general purpose compute devices, millions and millions of them out there. We need them to run all the daily tasks, financial calculations, everything we depend on. But we have the high performance computing and machine learning data center deployments growing much faster than the CPU deployments. And the energy consumption of these is growing quickly as well, partly because of the exploding demand, like I mentioned earlier. And we see these things converging out in the 2030 or so time frame, which really wasn't even comprehended in that SRC decadal plan outlook. So this is a big area of concern, and it's something that we believe innovation can help address. And so what we've decided to focus on is improving the energy efficiency of these compute nodes that service those markets by a factor of 30 over the next over the period of 2020 to 2025. So we announced this goal last year, and we focused, talking about system level thinking. We decided instead of just focusing on a CPU or a GPU compute device, we want to focus at the next level up in the system, which is what we call a compute node. And the most commonly deployed compute node today is what we call a 4P. We have 4 of these GPU accelerators, which can be used for machine learning or for high performance computing, and they are controlled and managed by a CPU server device here. So if we look at this, these are typically built on a single motherboard and co-located. And so we're focusing on the energy efficiency of this entire compute node. And we want to drive that efficiency as measured in performance per watt up by a factor of 30 by 2025. Relative to the industry rate, that's more than double the improvement. So the industry's definitely been improving. I showed you some examples from AMD's product lines, but that improvement rate is insufficient to meet the compute demands of the future without exploding energy and causing a significant environmental detriment. So we want to accelerate that improvement rate. If we tally up the amount of energy that saves, it's a lot of kilowatt hours. and that translates into a lot of metric tons of carbon dioxide and other metrics you can read there. This is a number not that we expect AMD processors to consume, but it's a theoretical that if all of the data center deployments were to adopt our 30x improvement goal, this is how much could be saved. And clearly, we want to have a big share of that market. But it's the point is it's a big opportunity. These data centers are large energy consumers. So we intend to hit that 30x goal, and assuming we do, that frightening trend in machine learning and HPC energy use is going to drop substantially, and as per the green line here. So this is the industry line, and if we hit the 30x goal, we end up in a much better spot. And obviously, we will be focusing aggressively on CPU data centers as well. So we're excited about this. These kind of big, bold goals, we don't know exactly how we're going to achieve them. I went through some of the tools in our kit that we think we can use: 3D stacking, lower precision math, algorithmic improvements, all these approaches, efficient caches. Some mix of those will be necessary to get there. It's a good way to rally the teams and the engineering teams in the company to focus on power efficiency and come together to deliver something that's really breakthrough. So we're excited about achieving this goal and the innovations that will be required to get there. And it's not just the compute devices themselves. As a company, we are absolutely focused on improving the footprint of our company operations, working with our suppliers to improve their operational efficiency, reducing the waste they generate in manufacturing our products. And we're looking to get to 100% of our supplier factories having a responsible business alliance audit and reducing their greenhouse gas emissions as well. So excited about the bold plans we have as a company and the technology required to get there. We love innovating. We need partners in innovation and finding solutions to these challenging problems. And pleased to be able to talk to you today. So that concludes my presentation.
First, thank you for a really enlightening presentation. I think you've really shown some of the dramatic challenges that are happening in compute, both in high performance and machine learning and in general, and where that's taking us from an energy perspective. And it's, I have to say, rather sobering. And you've done a nice job of pointing some of the directions that AMD is taking, and also some of the directions that academia might take towards helping things like the formats of data, architectural enhancements, 3D packaging. I'd be curious to understand from your perspective, what do you think in terms of achieving this very aggressive 30x goal you've set for yourself? What do you see as the highest tentpole? Well, like if somebody could hand you a magic technology, or at least the start of a magic technology, where do you think that the biggest single opportunity, especially coming from sort of new ideas, would be? That's a very tough question, I know.
Yeah, it's a tough question, and I'm more of a hardware architect, so I gravitate towards those examples and can talk to them in great depth. But actually, I would say it is in the algorithmic and software side, and adapting our software solutions to make more efficient use of the hardware. And that can be subdividing problems differently, and like I touched on, making use of lower precision math operators to accomplish the same result, which requires innovation, proper use of the system level architecture. So data movement is our enemy for energy efficiency, right? And simple programming approaches that split up the problem and then have to combine results in a central location to do the final computation. Those are inefficient. Right? So figuring out to be more localized, minimize the processor to processor communications, minimize the amount of memory use, keep things local on the silicon instead of moving it off to DRAM. All of those approaches, I would say, are probably the single biggest lever and the greatest opportunity for research and collaboration. Now we have a lot of exciting things on the hardware architecture side, which I would say is they're the sum of a number of smaller improvements that together add up to large gains. But I can't point to any one of them and say it's great. I mean, the 3D thing is obviously going to have an impact, and the matrix, the dedicated matrix math pipelines are great. We're going to see more and more of those, and don't want to keep too protracted an answer, but that's an example also of a software hardware synergy sort of approach, where we recognize the common loops and operators in software and implemented those hard coded in our compute devices. And so I look forward to more of those opportunities as well.
That's very interesting. Let me ask you a slightly broader question as somebody who has a view sort of from the top and at the system level. I alluded to earlier that, when you have some big innovation that sort of breaks out of an existing mold of how things are being done, it can be very hard to introduce it into product lines where it doesn't fit with sort of the existing paradigm. And so I'd be curious to, understand what is AMD's approach towards enabling those kind of things to be brought into play.
Innovation is difficult. I agree. I mean, we can look at things like optical interconnects, which have been on the horizon for many years, and they continue to largely be on the horizon, but they are intrinsically more efficient, and it's economic drivers that really get any industry and company over the hump and adopting new approaches. So the demand has to be there for these new, more efficient approaches, and then that drives the research and development to enable it. But what I would say, so that's kind of the glass half empty view, right? What we are doing, what I'm committed to doing, is trailblazing innovations that are ahead of their time, and so that they are ready to be adopted when all of a sudden the economic drivers are there for it. And so that's my goal, is to have incubation internally of some of these capabilities, and then when the time is right, we can be much more quick in deploying them. And that requires, and that's what academia is great at, having that longer term view of where things are going, and 5 years from now, what are some of the improvements that are needed, and then we can start on those earlier and be ready for them.
That's great. I'd like to turn perhaps to some questions that are coming in, and one that came up, and it's sort of very topical to the modern time. Since crypto mining and proof of work kind of energy consumption is growing heavily, sort of what are your thoughts in sort of addressing those challenges? And you could, and the question also asks about, the efficiency of current ASICs, but also things like the cooling challenge, addressing the cooling challenges for these kind of parts.
Yeah, I have to say, on the cryptocurrency mining, proof of work and those things, that is a big energy consumer. I know there are new currencies being defined and deployed that require less energy to mint new coins, but fundamentally it's just highly compute intensive, and there's not a whole lot in our toolkit to deal with that, other than having the best power efficient silicon that we can design, which certainly we're doing. And that creates a lot of heat. And I would say, immersion cooling, it's a reactive approach. It's kind of a necessary way to deal with the heat being dissipated without melting down the silicon. So it's not really a way to get to energy efficiency or to deal with this particular challenge. Special purpose devices, like I said, the domain specific accelerators are done right. They are intrinsically much more efficient than general purpose, right? So coins that get a lot broad adoption warrant special purpose accelerators to mint the new ones, and that certainly is the best way. But that's a risk if you're going to invest a large design team and pay for the silicon to do these things.
Sure. Another question that came in, and I'm going to ask both the question they had and something I was curious about myself. The question relates to, you're referring to the data formats being and sort of changing how the math is done, being a nice driver in terms of getting very high performance in things like ML training. And so the question first is, are those kind of data formats dial up, dial down, or do you have to architect your whole chip around it in terms of a particular data format? And the second question, or the related question to that, would be, if you're doing special purpose hardware for training and sort of data formats for training, which is as you mentioned, the very energy intensive part of ML, do those data formats traverse right over to general purpose hardware for the executing the train network?
Yeah. Okay. So a lot of good questions in there, and this is, I think, one of the a very exciting area for improvements and for a lot of innovation. So does a consumer get locked in? And that is a big problem, right? I mean, we have to choose when we design our hardware, how the transistors are going to be hooked up, and we hook them up to do certain formats of precision math. That's the way it is, and then the software has to adapt, and maybe the research and algorithmic innovations lead towards a different format than we chose to implement, and that's highly problematic. So there is work going into more adaptable data paths and flexible positioning of the decimal point, for instance, between exponent and mantissa. So there's a certain amount of adaptability we actually can put in areas like this, but we need, I think that's an opportunity for improvement. So because there's a tension there, right? We want to use the new formats, but silicon takes a really long time to design, and software evolves much more quickly. So there's a challenge there, and so we're putting as much flexibility as we can. So you mentioned the training and then the inference side, using the trained elements to accomplish the tasks of speech recognition or whatever. Those tend to have very different precision demands, and for training we have to converge the algorithm towards a good set of weights on all those billions of parameters. And that convergence time is what sets the energy cost and the expense of training the network. And so too low a precision and the algorithm doesn't converge. So that's the challenge that we have on the training side. But then on the inference side, we receive those parameters, and typically much lower precision can be used. And in fact, we go down to integer 8 or int 4 instead of 16-bit floating point for training. The precision used for inference can be influenced by how the network is trained as well. And so we can train a network for a specific precision of inference. So if we're seeing the most energy being consumed actually in inference, because let's say we're deploying a trained network out to 10 million different edge instances, or smartphones, well, that the energy used with high precision inferencing could swamp out the energy used to train the network in that case. So we can invest more energy in training a network that supports lower precision inference, and we end up ahead from an energy footprint. So a lot of interesting exploration needs to be done there, how to optimize this.
That's kind of very excellent detailed answer to the question. You mentioned a few places where sort of industry and academia can kind of collaborate and sort of making sure to be ready to absorb sort of new ideas when they sort of become viable by the driver, viable in terms of the market sense. I'd be curious to understand in these evolutions of these products, you've just sort of shown how they've gone along. As with a lot of the fab, the chip outputs and the fab costs, are the deployment costs of a new generation of systems for you rising dramatically with these sort of innovations, or can you kind of keep that curve flat, if you understand what I'm saying? Because if it just grows exponentially, you can't do it, period, right?
Yeah. The economics of developing these is very challenging, right? Because these new technology nodes are, not only is the cost per transistor flat or rising versus the Moore's law of the past, but the mask costs and the wafer prices to generate these devices is going up pretty dramatically too. So the barrier to entry for designing processors is rising, right? And it requires bigger companies to do it. The reason bigger companies can make that investment is because we amortize that sunk cost of developing it, manufacturing it across millions of sold components. So we need a sizable market to justify the development cost for these things. And that is at odds with what I just was saying, in that domain-specific accelerators are one of the best ways to improve energy. Well, as per that little bell chart I showed, domain-specific, they accelerate a small set of workloads, which means their market is smaller, right? So now instead of 10 million, you only can sell 1 million of these special purpose things. Sure, they're really efficient, but now their costs are going to be really high, right? Because you got to amortize over fewer. So we have a real tension there, and that's why I'm excited about the modular architecture that I briefly mentioned. I could go into great depth on how we're doing that, but when we can design small components, maybe 3 different accelerator types, and mix and match differing numbers of those to provide accelerations appropriate to a given set of workloads, the amortization of that sunk cost that I just mentioned can once again be over a much broader, much higher volume set of parts, because we're providing differentiated individual products by mixing and matching.
Oh, that's actually, and that is one of the challenges. That's really interesting. I'd be, sort of related to that note, I'd be curious to understand. You mentioned needing the space, needing the market, and the ability to make the chips. What do you see as the key partnerships across industries that are most important for better adoption of more efficient computing?
Yeah, well, yeah. So there are so many deployments of these compute devices, and into automotive, for instance, is a really big market, and the smart homes, and cellular base stations. There's just a huge breadth of deployment areas, and they have different power delivery, heat dissipation constraints. And so specializing our designs for these different markets requires collaboration with each of those segments to understand their needs. And to the extent we can design adaptable products that are right-sized in power and compute and cost for those markets, we'll be much more successful as an entire industry and ecosystem. And that does get back, once again, the modular architecture is a very powerful way to get there. And but yeah, there's a broad set of collaborations necessary, and that's another great function, I think, of academia is bringing different groups and voices and diverse industries together, because a lot of times it just takes talking together to see an opportunity in a way, like stuff we already have, in our toolkit, can be applied in new ways to help the problem. So.
No, that's very good. And maybe as a final question, as you said, there's barriers to getting these things out there. Do you have suggestions for incentives or ways to connect either with your sort of customers and partners in whether it's the automotive industry or the gaming industry or cloud, or with academia, that sort of would help lower the barriers to sort of getting innovations into the systems and then out to the customers?
Yeah, That's great. I mean, I know, foundries do multi-project wafers that help lower the cost of entry. So, they have one chip, and then, dozens of people contribute little pieces, and then the manufacturing costs are divided. So that's already in place. One of the things we found, I mean, we just completed an acquisition of Xilinx, the programmable logic company, which was a very big investment. But one of the reasons we did that is it enables adaptation. So field programmable gate arrays, right? They enable configurability for particular markets, algorithms, compute needs, and that enables us to more specifically address these different market segments. But the other opportunity it opens up is prototyping of new approaches and algorithms in an FPGA and programmable logic that is much lower barrier to entry than designing a custom piece of silicon. Sure, it runs slower, but often, I mean, it's within an order of magnitude of custom silicon, and so it enables a genuine look at whether this is a good idea or not. And so I do think that's a very promising area, using programmable logic arrays.
Very interesting. Well, I think this session has given a lot of food for thought, both where the trends in compute energy are going, and what are how the challenges are evolving, and some of the directions that can be taken to attack those. And so, first of all, I'd like to thank you for a really stimulating presentation, and to the audience for some interesting questions. I think there's clearly a lot to be done and a lot of challenges, and I'm glad to see how seriously AMD is taking them. So thank you. I will just let everybody know that we will be taking a short break, and then we will be resuming in approximately 15 minutes for the next section of our workshop. So thank you very much.
Hey, David.
Shall I start? All right, so I got them. Go ahead. Let me see. Yeah. Hello, everyone. Welcome back to the MIT Climate Implications of Computing and Communications workshop. We are in the 6th and last session where we will have a panel discussion to share ideas and ongoing work on novel architectures and novel hardware for reducing the energy consumption associated with computing. And you have already heard a lot on the energy and sustainability implications of computing in this workshop, but I will start by reminding one key number. That is, the goal in the field is to improve the energy efficiency associated with computing by more than 1,000,000-fold. So that's the target that was recommended by the workshop and report that was provided to the field by the Semiconductor Research Consortium in the last year. So more than 1,000,000-fold. Where is this number coming from? It's coming from the fact that the field, us all, are working on improving the capabilities of computing, in particular in contexts of AI, where we want to come up with computers that can sense, perceive, reason similar to the human brain, and do this in an energy efficient way. And if we look at the compute energy trajectory from the last decade and into the next few decades, if we continue with the existing trajectory of compute energy, by 2040, we are supposed to hit the world's energy production capacity. So the increase in compute energy and compute demand has been increasing at a much faster rate than the world energy production capacity increase. So of course, this is not sustainable. One will either have to sacrifice from computing in order not to be unsustainable in terms of energy demand, or we have to come up with fundamentally new approaches, both from hardware and software fields, to improve the energy efficiency in computing. And again, the target is very ambitious, more than 1,000,000-fold improvement in energy efficiency. And this requires breakthroughs all the way from materials and structures to devices, circuits, architectures, to software algorithms and applications. So it needs reinvention of all elements from bottom up that go into defining computing and computing efficiency. And this naturally then needs contributions from multiple disciplines, including computer engineering, electrical engineering, as well as material science, physics, chemistry, and learnings from neuroscience that can guide the architectures towards being more bioplausible, for example. And we cannot cover all of this in this panel, but a few new approaches that we can remind here include in-memory computing with new unit building blocks, as well as new interconnects, charge-based electronic or non-charged based devices where the readout can be not only electronic, but also magnetic or photonic properties. To achieve this in a dense, high-speed, and low-energy manner is being the goal for all. And inspiration from neuroscience to guide the architectures that can go into these computing platforms, inspired from how brain works, achieve brain-like connectivity with brain-like energy efficiency, which is the most energy efficient computing machine that we know. And scalable quantum computing is also a promising technology that in the future can give us the needed energy efficiency with computing. And all of this have to be supported with novel materials and process invention and development. So with that, I will go into introducing our panel, which includes world experts on some of these topics that will share their ideas and expertise with you. So I'm assuming my slides are out of the picture now, right? Okay, yeah, because I cannot see both at the same time. Great, so let me introduce our panelists next. As I said, we have a wonderful set of panelists who bring their expertise to discuss with us on novel paths for reducing energy consumption associated with computing. So first is Dr. Jesus de la Lamo. Dr. de la Lamo is the Donner Professor of Electrical Engineering in the Department of Electrical Engineering and Computer Science at MIT. He is a distinguished expert on nanoelectronic devices based on compound semiconductors and ultra-wide bandgap semiconductors, and also on novel ionic and ferroelectric devices for artificial intelligence accelerators. Our second panelist is Dr. Takashi Ando. Dr. Ando is a principal research staff member at the IBM T.J. Watson Research Center. He has made pioneering contributions from early research to productization phases of high-K metal gate technology, and this has enabled high-performance server chips from IBM since the 32 nanometer node and many of the early smartphone and tablet mobile chips. And third is Dr. Heike Riel. Dr. Riel is an IBM fellow and head of science and technology and lead of IBM research quantum in Europe and Africa. She is a distinguished expert in semiconductor electronic and optoelectronic devices, nanotechnology, and nanosciences, and she focuses her research on advancing the frontiers of information technology through the physical sciences. So welcome again, Dr. De La Lamo, Dr. Ando, and Dr. Riel. So I will start by asking questions, and we can open and expand the discussion from there. So first, can you tell us about the technologies that you each are working on that has the potential to reduce the energy and CO2 footprint of computing in the following years to decades? So would any of you like to volunteer, or if not, I can pick one of you to start. I see Dr. De La Lamo nodding, so I will.
Thank you for inviting me to be part of this panel and allowing me to do this college here. Yes,
Dr. De La Lamo, I don't know if it's my speaker, but I think there is some noise in your voice connection.
Is it? I don't know what to do.
Yeah, I see a note from the producer that maybe your mic needs some troubleshooting.
Why don't you go to something else?
Then I will go next to Dr. Riel as Dr. De La Lamo fixes the microphone connection.
Yeah, thank you very much for having me on the panel. It's a great pleasure being here. And the energy efficiency, which is part of this meeting, is really the key challenge in computing. And this is not something new, but I think the community has been working on the energy efficiency over many years. However, it's becoming more and more severe. And if we look at some of the I just want to give an example, also demonstrating that this is not something new. And I think this example, if you look at high-performance computing and you compare today's high-performance computer, for example, the IBM Summit system, which you may have heard of, which is the 200 petaflop system. It consumes 15 megawatt, which is quite a number at peak performance. If you go to the system before the IBM Sequoia, it had 220 petaflops, like a factor of 10 less performance, but it only had a factor of 2 less power consumption. So you see already within the technology development, there is a lot of improvements in order to improve the energy efficiency, and it's becoming more severe. With the future of computing, where we have different areas, and actually IBM works on all these different areas, and I let it to Takashi to talk about the AI part, but also in the conventional silicon part, in the entire stack, we need to improve. So if you look at this HPC system, it really starts from the transistor and it goes up into the entire stack, whether it's silicon photonics, which has been brought in, whether architectures, etc., to not only increase the performance, but also reduce the energy which is consumed. And we are, as you mentioned, we are also not only working on AI accelerators, but we also work on the classical systems and also on the quantum computing. And in all of these things, we want to save energy. When we look at quantum computers, which I'm working on, then quantum computers, it's of course a completely new technology, which has the potential to solve problems which classical computers cannot solve. So that's one part, that you can solve problems which other classical computers cannot solve. And this means you get higher accuracy for certain problems, or you get also faster speed, or you can solve problems which can't be solved. Now let's look at the cases you want to test. No, it's still bad, actually. I think yes. So let me continue. If we look at the energy a quantum computer uses, and perhaps people mean, oh, this is a big system that we see in these pictures we know and have in our mind. Perhaps it consumes also a lot of energy, but that's actually not the case. Although we need to cool down the quantum processor to 10 to 15 millikelvin, which is very low, it does not actually take a lot of energy. And at the low temperature, the devices are actually in the superconducting regime where you have almost no dissipation. So if we look in the detail, and I think Dario also brought this, mentioned it in his presentation, then you have like 10 to the minus 16 watt per 2 qubit gate at 5 gigahertz for 100 nanosecond per gate. And so if you do the math and you look at the different energy consumption parts, I mentioned already the supercomputers, which needs megawatts, tens of megawatts. Then if you add up the energy a quantum computer needs, then it's a bit of the cryogenics, like 25 kilowatt. You have the room temperature control electronics, which you need, which is currently at 6 kilowatt. But also here, there is a possibility to improve. And then you have also like classical compute energy, which you need. So you come to about 35 kilowatt, which is really much lower than a supercomputer, and with a chance that you can solve problems which a classical supercomputer cannot solve, and also with having the chance to solve problems more accurate or much faster.
Thank you, Dr. Riel. That was very helpful, both to hear that innovation at different levels of computing platforms are needed, but the numbers associated with quantum computing being 3 orders of magnitude lower, 3 to 4 orders of magnitude lower compared to the current supercomputers. That's very helpful to remember. Numbers stick, right? Thank you so much, Dr. Riel. So let's give the word to Dr. Ando next.
Hi, thank you for the introduction. Can you hear me?
Yes.
Okay. Yeah, as Dr. Yildiz introduced, my original background is the material development for the CMOS logic scaling. And that continues to be very important because no matter what new computing paradigm we introduce, the key is to tap into the existing data, which is growing exponentially. So we need a very dense memory and logic to be able to communicate with the data, large amount of data. So we think that the continued scaling of the baseline technology is important, and there's an still ongoing effort on that. But in the meantime, we need a new paradigm of computing. And my recent focus is to develop a new non-volatile memory, which can enable the deep learning acceleration with an in-memory compute. And what we believe is the existing non-volatile memory out there is developed for the memory application and not necessarily customized for the deep learning. So what we are doing is developing a new material and device from ground up that is more suitable for the deep learning acceleration, and build that into the state-of-the-art CMOS technology, such that we can prototype and show a proof of concept that it can be better than the incumbent technology. And for that purpose, we are having a consortium called AI Hardware Center, where we are working with the partners from across the many layers, like tool vendors and the device company and the metrology company. So we are making an ecosystem within the industry. And also we are collaborating with academia, like with MIT. I have been working with the faculty members for several years now. But in order to make an innovation from ground up, we think that it's very important to collaborate with universities. So we are making an ecosystem within the industry as well as with academia to drive this innovation.
Excellent. So thank you, Dr. Ando, hitting on this new non-volatile memory approach to low energy computing. So, and next is Dr. Delalamo. Hopefully,
Can you hear me now?
Yes.
Can you hear me now? Okay, good. We're back. Good. Thank you very much, Birgit. Again, I'm delighted to be here. Yeah, there are three aspects of computing that my group has been working on regarding the pursuit of ultra low power electronics. And first, to perhaps come from the wall into the machine, there is all the power electronic side of things. Obviously, the computer is going to burn a lot of electricity, and the management of the electrical power coming in and being prepared with the right voltage under the right conditions in the different subsystems is extremely important to do it in a very efficient way. And for that, there has been great progress on wide bandgap semiconductors. And looking forward, there's a lot of interest in ultra wide bandgap semiconductors to do more efficient electrical power management. So gallium nitride today is an emerging technology that looks extremely promising, which is starting to find its application in many systems. Looking forward, there are ultra wide bandgap semiconductors that also look very promising that could potentially be even better than gallium nitride, such as gallium oxide, diamond, aluminum nitride, etc. So we have some activities in my group in that area. The second aspect of computing that is here to stay and is going to continue to require improvements in energy efficiency is the baseline CMOS. So even if we innovate new computing architectures and systems, CMOS is here to stay. It's going to continue to do a lot of the basic logic and is going to therefore continue to burn a lot of electrical power. And we need to continue to do our best to enhance the energy efficiency of what one could call conventional CMOS or roadmap CMOS. And in that regard, my group has been working for many years on various technologies. For quite a few years, we had a big effort around the world on indium gallium arsenide electronics as an alternative to do logic with at very low voltage. That didn't quite pan out for a variety of reasons, including manufacturing reasons. Today, there is still interest on tunnel FETs. These are tunnel BESS transistors, which offer the potential of working at very low voltage. And so I also have research activities in this area. And then the third aspect of all this is what Dr. Ando has just mentioned, which is new technologies for new computational paradigms to develop accelerators that are specialized on the specific computing applications that are going to be quite pervasive, quite energy consuming, and that we want to optimize. So we also have activities actually in collaboration with Dr. Yildiz also on new synaptic devices to essentially design, implement non-volatile analog resistors that can form the basis of analog neural networks or much efficient matrix multiplication. So I have two projects there, one with Bilge on electrochemical devices and a second one on ferroelectric synapses. So this is a fantastic area of research, and we have many activities, and it's a lot of fun, actually.
Excellent. Yeah. Thank you so much for this first round of answers where we touched advancing existing CMOS because, like Jesus mentioned, it will stay around, so we need to still work on its scaling, and quantum computing, as well as novel memory concepts, electronic or ionic, for analog energy efficient computing. So that's great. Then let's go to our next question. So we heard about the high-level description of these novel directions that you're pursuing, and I wonder if you could give us some specific examples of most exciting recent developments in these respective fields. So we can go in any order you would like, and maybe we can reverse this time and start Jesus first. Yeah.
All right, thanks. Thanks, Birgit. Yeah, it's the fields. These fields are moving very fast, and there's a lot of new results. I think I would mention, if I have to choose one, the recent research that we have been doing together, Bilge, in the area of proton intercalation devices, which are these type of analog non-volatile resistors that can be programmed to take specific values of the resistance and can be held for a very long time. Bilge and I and other colleagues at MIT have been working on proton intercalation devices in which we're able to move protons, these are the ions in question, into a semiconductor, and then that changes the conductivity in a programmable way. And this is like a mini battery device so that you can put the protons in or take them out, and the device will hold them in memory. And I think the exciting result that we have recently is that we have now been able to create a system that is entirely CMOS compatible, both in terms of the materials that are being used, in terms of the process technology that is used, and in terms of the temperatures, the temperature budget that needs to be used to be compatible with the back end, with the later part of the CMOS fabrication process. So this is tremendously exciting, and I am looking forward to making great progress in this area.
Thank you, Jesus. And I'm so excited to hear that you picked this particular example among all the exciting work that you do. Of course, I can sound not objective, but very exciting to hear that. Great. So thank you again. And Dr. Ando?
Yeah, so as I mentioned, for the new computing paradigm, both scaling and the new elements are important. So on the scaling part, the important milestone is IBM proposed a new device architecture after FinFET to be a stacked nanosheet several years ago, and now it's adopted in the industry, and now it's becoming a new next generation structure. So that kind of continued scaling on the CMOS technology, that's one very important milestone to continue this effort. And on the new element part, I also collaborate very closely with Professor Yildiz. So I want to mention that, but it's already taken. So instead of picking one specific one, the overall in the compute in memory field, several years ago, the technology itself was only accessible by limited few people. So we didn't see much prototype or large scale demonstration. But in the last couple of years, what we have seen is the foundry becomes available and the technology itself becomes widely available, including for the academia members. So we now see many prototype or actual demonstration at reasonably large scale. So that's the very exciting progress in the field of demonstration of the new computing paradigm.
Becoming more widely accessible and also motivating a wider spectrum of researchers, perhaps.
Yeah, it's growing. The field itself is growing because of the accessibility of the technology.
I am one example, right? I'm new for this particular research area, but it has been very exciting for us to learn and contribute to. Great. Thank you, Dr. Ando and Dr. Ril.
Yeah, so it's a very difficult question because you say we should pick only one. And I think in this field, there are really so many different things going on. And if I look at the, Takashi already mentioned the nanosheet transistors, which enable the 2 nanometer node, and also the energy efficiency, which is being achieved with going to that, is really super exciting for me, because I have started 2004 the nanowire project within IBM. And so we studied to grow silicon nanowires and 3.5 nanowires, and seeing that this gate-all-around architecture now made it to 300 millimeter and being really for the next node the solution is really exciting. And just to follow up on this, actually, when we started with nanowires, we worked on vertical nanowires because they were easier to grow at that time. And now seeing also that also on 300 millimeter vertical nanowires are built because they have the advantage of the gate length, right, of the short channel effects. Also here, the energy efficiency, which is critical because you have the off state at zero, the off state is much lower and things like that. So it's really exciting to see that these things come into fruition, but it also shows that there is a long lead time until it really works out, with a lot of hard work in between. I want to actually also mention another area which is more future looking in the classical world, or for the classical compute, which are making use of new materials of topological phenomena. Because topological phenomena are something where I think the physicists can play a lot around, and they come up with great materials and great ideas how this can be used. And just recently seeing that, I mean, a big problem in classical is that the resistivity of copper is increasing with making the line width smaller, the dimension smaller, which is actually getting a big problem because it creates heat. And so seeing that there are other materials making use of topological phenomena where the resistivity stays constant when you make the thing smaller, and they actually will win when we have to further downscale the line width, is really, I think, very exciting. And there is so much material research also still to be done in order to better understand, in order to find new materials, etc. The AI hardware, you have mentioned the project, so I don't need to go into this, but I think there are also many interesting new ideas which are coming up, but I think there is more needed, and they also, of course, all have to make the proof of reality, whether these are not just great ideas, good for a paper, but also for real implementation. And if I look in quantum, this is, of course, a very dynamic, very exciting field, quantum computing. It's developing now really fast, lots of progress over the last years, seeing it developing from 5 qubits in 2016, now having processors with 127 qubits, and following the roadmap which IBM Quantum has published, then this year we want to demonstrate 433, and then end of next year more than 1,000. So there's a lot of progress coming up. And of course, this all is rooted into new technology developed, further developing the technology, but not only the hardware, but also the software and the entire system has to be optimized. And important is here for us to increase the scale. This means the number of qubits, the quality of the qubits, which again entails a lot of materials know-how, device know-how and optimization, system optimization, and also the speed, that because in the end you're interested in how fast you also get your result of your calculation. So there's a lot of progress which has been made and is going on, and seeing this is really very, very exciting.
Thank you for sharing that, Dr. Il. So a few things that you have said, or maybe let's say if we summarize what we heard here, the advancements in the quality and number of qubits in quantum computing, and new ionic or electronic devices for non-volatile analog programmable memory for AI accelerators, as well as the initiation and now implementation of the 2 nanometer node, right? So these are all very exciting examples that you shared. And the years that you quoted, Dr. Il, brings me to my next question. So this particular example of nanowires that were initiated back in 2004, you mentioned, now are making their way into the implementation as the next generation node. And so that's about 18 years, right? So let's take that as an example, but going back to these exciting other, let's say, futuristic developments, what are the timelines that you think are associated with them? And again, a lot of hard work during that timeline that will have to go into them, from the current state to implementation in technology and applications.
So are you asking me or no?
In any order. So if you would like to take a first shot, I get that's perfectly good.
So I actually used a lot of different examples. So I think if I look at the topological materials and devices, right?
Topological materials for interconnect. It's a wonderful example. Right?
Yeah, I think that's something where, I hope that topological materials and devices will have impact in many different areas. And I think the example I've given in the resistivity may be one where, this could be in like a, I would say,
interconnects, for example,
5 to 10 year time scale, right? But this is just a really rough guess, because we all know that we are as researchers typically too optimistic. So, yes. And then there are, of course, also using these phenomena for other applications, which still need a lot of basic research and technology development to make it then into some product. And I think when I look at quantum, there is continuous improvement, and these things are directly integrated. There is also analogies from the semiconductor things which we can bring in by optimizing in engineering. And it also needs, in the end, the full system. I think that's important that we always have the full system also in mind. Because in the end, it's not only about the qubit or not only about the AI hardware chip or the core, but it really needs the entire system to be more energy efficient than what we have and also show higher performance of what we have.
Great, thank you. And Dr. Ando, your thoughts about the timeline?
Yeah, so I mentioned about the analog memory elements for deep learning acceleration. And in that field, we are already seeing some use case for the deep learning inference, right? So it's already happening, but I think that the current stage is that it's similar to new non-volatile memory finding appropriate space within the memory hierarchy. So I think the incumbent digital accelerator is so powerful, so I don't think the replacement will happen. So it's more like finding a right application space where analog AI shines, and finding such space is the current status, in my opinion. So I think for the deep learning, inference using analog memory is for inference. That I think we are in that stage, and in the next 5 years it will continue. So once appropriate application space is fine, we will see more wide use case. But on the other hand, for the deep learning training, what we found so far is that the requirement on the analog memory is so drastically different from the conventional memory. So we think it takes a longer time, and we may need a more fundamental change in the device, not picking the existing memory, but we may need to develop a new memory. So in my opinion, that I expect that to happen longer time. So it may take 5 to 10 years is my outlook.
5 to 10 years. So we heard it twice now. Good.
Yeah, but for inference, I think we are already seeing something, right? Yeah.
For training with more data intensive aspect of the process, more time needed.
Yeah, some delay, but yeah.
Yes, but it
that's
will
my
get
outlook.
there. Yeah, great. And Jesus?
Yeah, well, we don't do products in university, so I can only talk as an observer of the time that it takes for new technology to reach the marketplace. And if you look in this line of business in the area of microelectronics and you look back in history, I think on average, it's taken 10 years from the point that a technology is demonstrated in the lab until that technology eventually reaches out the marketplace, is put in high volume manufacturing. I think Heike mentioned a few minutes ago just how far back she was already working on nanowires, silicon nanowires, and it's only now that they are in 300 millimeter and hopefully very soon in volume manufacturing. So, and this is for technologies that we see them coming in our roadmap that is relatively well crafted. We are not talking here about technologies that don't quite yet have a roadmap for them to be introduced for reasons that Takashi just mentioned, right? In some cases, it's not clear how they're going to enter and how the competitors, the other competing technologies could be used. So we have to be ready to be here for a while to push these technologies forward, and hopefully eventually some of them will reach the marketplace and will make a difference.
Right. Yes. So maybe we can talk a bit more about this last point, that there are uncertainties for which applications will be the best targets for these new technologies, and there are technological challenges along the way that we have to work on. So could you elaborate more on that latter next, that this will take time, but what are the key challenges that the field has to work on, either specifically or from an approach perspective?
Should I start?
Why not?
Okay, all right. So I think, 2-3 years ago, as I saw emerging this whole area of analog neural networks and analog computing, I decided that I wanted to look into it and try to contribute. And what I found is that we have different levels at which one has to act for a technology to eventually reach the marketplace, right? Materials, devices, circuits, architectures, algorithms, etc. And what I found is that in this new line of computing, there are no clear interfaces in between the different abstraction levels, as we have come to understand and accept and appreciate in, say, CMOS conventional logic technologies. And the lack of these nicely defined interfaces between different abstraction levels means that a specialist such as myself at the device level can't just simply operate at the device level. We must be able to understand what happens at higher levels of abstraction and at lower levels of abstraction, which is why a couple of years ago we started working together, because it was also very clear that to really make a difference in this new area, we were going to need new electronics based on new material systems, working on operating with different physical principles. And so it was clear that we alone, sitting in our area of expertise, could not really make a difference. And that is why, well, luckily we started working together, where you guys brought the materials understanding and the fundamental concepts behind these proton intercalation devices. We brought in our expertise in device scaling, in device integration, device technology, and we're doing great fun stuff. So I think one of the challenges here to abstract this is really dealing with the lack of well-defined interfaces between the different abstraction levels for folks that are experts at different levels to find a way to work together. It is difficult. It is hard. We need to overcome that challenge.
Right. So it sounds like you're saying we have to re-establish interfaces between the different levels of work that has to go into completing the whole system as a new and energy efficient platform. Okay, so because like you said, the current technology is well defined and those interfaces have been established over a long time period and they are working well.
Yep.
So someone working on semiconducting materials topic knows which device person to talk to, the device person knows which circuit person to talk to, and so on. But now everything being reinvented needs to reestablish those interfaces, I think.
Right, and we have a language at the interfaces that's well established.
That has to be redeveloped also. Right. Yeah, that's very good. Yeah, so other perspectives from Dr. Riel or Dr. Ando?
Yeah, so for me, the biggest challenge is that at the high level, for the deep learning area, what we are trying to replace is not the saturated or mature area. The digital accelerator is still a very hot area, which is growing exponentially every year, right? So the replacement of that is really difficult because it's a moving target and it's still a growing area. So in order to show usefulness over the digital requires demonstration at scale. So this is a new paradigm and new technology, but proof of concept is not enough. But we also need to show the scalability at the same time, because we are trying to replace the exponentially growing new field rather than replacing the mature technology, right? So showing the proof of concept and scalability at the same time is proven to be very challenging, and that's where we put more resource to really enable.
Yeah, that's a very good point also. So maybe in the field we produce perhaps more proof of concepts and than those that are actually scalable. So to identify those that can be scaled up and to demonstrate them is what you're saying.
Yeah, and in order to do that, I think we need to expand the ecosystem and work with players in different layers of the stack, like not only device but also the software and applications.
Right.
So I think larger, more concerted effort across the entire layers will be needed to really enable that. But that the scalability and the proof of concept at the same time is the biggest challenge to me.
Right. I guess this is the case in every technology, right? So here we are talking about energy efficient computing technology, but in energy conversion and energy storage area too, the challenge is not only to demonstrate proof of concept in the lab, but to be able to demonstrate that it is scalable, it has enough production rate, it has enough capacity to be technologically viable.
Yeah.
So
I think in the CMOS scaling era, the roadmap was clearly defined, right? In that case, we can do proof of concept, and then industry can take the nugget and
the
put
target
that on
is
the roadmap.
there. The target
but
is
now we are defining stage of the roadmap itself. Therefore, the nature of the collaboration between academia and university needs to be longer term. And
Yes.
I think that is the biggest challenge that I see for this new field. But that's also an area very exciting for the new innovation.
Right. Great.
I think following up on Takashi, I think it has changed when you go back like 10, 15 years where there was a silicon semiconductor roadmap. It was clear what to demonstrate over the next couple of years and what's need to be done. So all the different advancements which had to come together, whether it's lithography, whether it's material, whether it's the transistor, whether it's the back end of line, it all was kind of clear what needs to come together at which point. And it was like one general processor. But right now, with getting more energy efficiency and more performance out, having all these different options, it's also more difficult to develop all this in the holistic manner that you can really also use it in the end, right? That you can integrate it in the system. And so finding the right path of making it still feasible to develop this diversity of different things for different applications, and still making it in a way that it allows companies also to create some return of investment, because that is, I think, this is itself is a challenge, I would say, right? And then if I look at quantum computing as the big thing here, the big challenge, and also the big thing and milestone we want to demonstrate is quantum advantage. To say, okay, this is one example where quantum computers can solve a problem which cannot be solved by a classical computer, or provides value to companies. And of course, to reach this, we have to improve what I mentioned before. We have to work on the scale, on the quality, on the speed. And then you can dive into these things individually, and you find little different challenges which have to be solved on all the different levels, from the material to the systems architecture.
Right. So thank you for that. And I think a common point that I'm hearing from all of you is that everything at different levels are being reinvented, and we have to reestablish connections, develop these in parallel, and not only show them individually at proof of concept level, but scale them, connect them so that they become a viable technology. And that's a big challenge, right? And you also mentioned that like different disciplines, different people have to come together to work on these. And maybe that's a good transition also for me to ask, what do you think about leveraging interactions between academia and industry more closely? So we're at MIT, we're already very lucky to be able to collaborate with industry, including IBM, new colleagues, and it has been really exciting for us to understand the challenges and work with you to advance these technologies. So what are your views about maintaining that, flourishing that, advancing that for overcoming these big challenges in the field? I guess through this interaction, we're also both learning how each party works. Right? So industry has a technology target, and academia maybe comes from, again, more proof of principle level. We understand what the industry's goals are and challenges are, and maybe industry learns how the academia works and tries to leverage that. And what are your views about getting the best out of that interaction? Maybe I
can start and give my thought. I think what you mentioned is really very important, that the collaboration is providing many different synergies for everyone, and many win-win positions, because on one hand, it's important collaborating from the university side to also fully understand what are the challenges, right? That you also go after the right things that are in the end also useful and have an impact. But on the other hand, it's also from the university, I think, very important to create the basic and fundamental understanding of the things, because only if they have the basic and fundamental understanding, then you can really fundamentally improve things or create new things. So I think that's a really very important part. And that's something which is more and more difficult to also do at a company. So the collaboration here can be really very fruitful. And so I think there is also not the shape or form of a collaboration. It can come in really many different flavors. And in the current world where we really have to be very dynamic, very agile, very fast, and there are so many different opportunities, of course, then collaborating provides to everyone also the speed and the agility and more impact.
Thank you. That's wonderful. And Dr. Ando?
Yeah, so I have been working with academia for the last 15 years from the industry side, and I think the nature of the relationship has been changing. Yeah, as I said, when we had a roadmap and we are working on some technical topic, the collaboration can be short term, like 1 year or 2 years, and when the student graduate, we can stop. But as far as we have good publication, that was a good collaboration, and industry side can take the key parts from there and go on. But as I said, we are defining stage of the roadmap, and in order to show usefulness over incumbent, we need to prototype instead of just publishing, right? So that requires longer term collaboration. So I think what we are looking for is a longer term relationship, and also from publication oriented to actual demonstration or prototype oriented in my area of research. So that is kind of a change I have been seeing over the last
And that's
15 years.
also consistent with what you all said, right? This is so new. The targets are being defined along the way, and that renders the challenge to be longer term and the interactions to be longer term too. So yeah, that's helpful. And maybe we can hear from Dr. Dell'Alamo the academic perspective.
Looking from the academic side, I think a motto of MIT could be the dignity of useful knowledge. We really have a lot of respect at MIT for knowledge that is new, is true contribution to the knowledge of the world, but it also is useful. And we can work, particularly in this new area where we are talking about new material systems, new physics of operation, new device physics, etc. We can work on many different kinds of problems, many different material systems. We need the guidance from industry to tell us what lines are likely to be most promising to impact the world. We have a vocation to impact the world. And so that guidance that comes from industry is truly essential for us to be relevant, which is something that we really, really want. So I'm delighted with the very close collaborations and long-term collaborations that we have with IBM, because they're really helping us to pick up problems and directions that are particularly promising.
Great. So what I'm hearing is that the guidance on the important problems from industry is absolutely important for academics to focus on the right problem, and it's helpful to industry to leverage the novel and perhaps deeper science and engineering that could arise from academic work, and redefine these targets and boundaries together. Great. So that was very interesting discussion. And the next question I want to ask is, how do you think we can leverage what the field learns from how the brain computes, right? So the most energy efficient machine is the brain. So it's pretty much an electrochemical machine of taking data, making sense of it, and taking actions based on it. And there are a lot of very exciting advancements going on in neuroscience, experimental and theoretical neuroscience, in trying to understand how the learning and processing works in the brain. And what do you think we should do from hardware for computing side to interact with and learn from and translate to hardware from neuroscience?
I think it's actually the best question. It's really very, very hard to answer. Because we know the brain is super efficient for some tasks, not for all of them, right? Because for some tasks it's completely not useful.
Yes. It's
But,
true.
and
So
so, but
whatever it can do, it does it very efficiently.
yes, but for some of the tasks, exactly, it's very, very efficient. That's for whether it's image recognition and all these type of things, right? And so it only needs 20 watt. So unfortunately, we have not yet fully understand how the brain really works. And there is research going on for many, many years. And there's a lot of things going on for trying to image it, trying to model it, many different ways of how to understand it. But we are not yet that what is known can be really applied to something which we build. So, I mean, if you look at the accelerators Takashi mentioned, right? And also what Jesus and you mentioned, then it's still kind of trying to solve mathematical functions in a better way, which are part of deep learning, machine learning, etc. Right? I mean, in the end, what we do right now is like matrix multiplication, trying to make it better, faster, more efficient, parallel, etc. So this is not yet. I mean, bluntly, that is not yet mimicking the brain.
Mm-hmm.
And mimicking the brain, what people have done with the spiking neural networks, that's it's kind of it's a start. Let's put it this way. But there is still like learning algorithms and all this is missing. So we are really at the very, very beginning of really mimicking or building something which works like the brain.
Mm-hmm.
It's exciting and it's exciting research. And this is actually also part where I think the universities can be really strong, because I think for the companies, it's a bit, okay, I can't use it in the next 20, 30 years, probably, most likely. But it's a very fundamental problem which should be solved. And also with the techniques, like the imaging, which is getting better. You know, what we learn from looking at the brain under different functions, from the modeling capabilities which we have, and all this, bringing this together, it's a really huge task. But I hope that step by step we come to a solution.
Mm-hmm. So maybe what you're saying is that this is yet another interface that we need to establish and build upon. So maybe the traditional computing architecture never cared about interfacing with neuroscience. It's materials to devices to circuits, architectures, algorithms. But the interface with neuroscience was not needed perhaps until the growing interest in intelligent machines, but also to do that in a very energy efficient way. So what can we learn from the brain in
Yeah. And also like I mean, directly interfacing with the brain, right, is still also,
yes,
I would say, in a very rudimentary way what we do.
yes, yeah. And maybe some of these devices that we are working on for analog non-volatile processors, we can use them to emulate, let's say, the biological process, but maybe in the very long term, they could also interface with the brain to assist the neurological side of the process, right? Yeah, and Jesus?
Yeah, I don't have much to add beyond what Heike has said. I know nothing about neuroscience. As you know, we are trying to we're working with colleagues in neuroscience at MIT. This is a good topic for a university like MIT, where we have world-class expertise in many different domains, and we can come together and try to do something together. And we are finding, talking about the interfaces again, that we don't talk the common language. We don't talk a common language. It's difficult to communicate across the boundary. I have to say, though, that on the educational front, we are doing things, and I think this is relevant. So maybe 2-3 years ago, MIT introduced a new major, which is at the interface between electrical engineering and computer science and neuroscience. I think is labeled 6, 9. 6 is electrical engineering and computer science, 9 is neuroscience. And the first graduates are coming out this year, if I know this correctly. So this is what we need, right? That we realize that at that interface, there's a lot of good work to be done, and we need to prepare students that are specialized on the interface, that can understand both languages and serve as a glue for these two big fields to come together and work together.
Yeah, I agree. So training the next generation at that interface would be very helpful.
Yeah.
Those who are already in the field and have been traditionally trained in the separate disciplines maybe find it hard to communicate, but maybe the next generation, it will become natural to them if they are already trained at the interface.
Yeah.
Right, that's very exciting. And Takashi, would you like to add?
Yeah, I think I echo with Heike, and I don't have much to add, but yeah, I agree that we are mimicking a few features of brain, but not necessarily implementing the mechanism or secret of learning itself, right?
Right.
So it's very difficult to go beyond just the energy efficient deep learning at that stage. That's very important, and we should push that. But in parallel, we need to learn more from the learning, the mechanism or secret of learning itself. That needs to be a parallel effort that we need to always continue.
Right. What are the learning rules, and can we translate them to hardware implementation? Right. Something we should push for together. Thank you. Yeah, I think we covered all the questions that I wanted to specifically ask you, and I can leave it open to you now if you would like to add any additional points or ideas or questions that you would like to pose, and any last words that you would like to share.
Well, since you give us a chance, Birge, I'd like to put a plug for a new program that we are launching at MIT, which is the MIT AI Hardware Program. We are about to make it public, perhaps any day now, which is a new consortium of companies that are interested in AI hardware, that are interested in connecting to a community at MIT of folks at the different levels, as we have been discussing in this panel, that are relevant for AI hardware to bring us together and to start working on these interfaces and start working together to try to innovate future hardware to make AI vastly more efficient and capable. So it's about to launch. We are excited to start working together with a number of companies, but we are open for more companies if they want to join us.
Very exciting. Thank you for sharing, Jesus. Excellent. Great. And Takashi, Heike, if you would like to.
Yeah, so I believe many students are also listening this, right? And yeah, when I speak with students, in their mind, AI is all about coding and application, right? But I want to emphasize that true innovation comes from device or material or hardware, right? And it's an exciting field. So I want to share that with a student working on hardware. And
excellent.
I want them to feel encouraged. And I think burden is on us to actually show it's cool. But I think at least I can guarantee that it's an exciting field where they can grow. So I hope many more students working on hardware joining this journey.
Right. Physics and hardware AI is super exciting, and we need fresh and engaging and curious minds to join this. Exactly.
So I want to add, actually, because I think that the innovation or the biggest innovations will come from people working across the entire stack together. And we gave the example of understanding the brain, where you also need all the different people kind of working together to really then bring transition something into hardware. And I think also of everything which we right now do is building more system optimized solutions, which are more energy efficient and more performing for this specific task. And the innovation is really now more at the interface, where the different, people, the different problems come together. We have over many years worked everyone in its own island, right? The device people, the circuit designers, the software people. And I think now we can't escape. And that's now we have to really learn a bit the language of the others and do step-by-step work to closer together to optimize the system. And that's also, Takashi, for the students important, right? You already touched the students, that you try to open your view a bit and you learn also about the other side, what they're doing, and be able to talk to each other and form really multidisciplinary groups in order to tackle the big problem which we have, because it's a big problem. We have to get more energy efficient.
Great. So I will conclude by saying that interface is the key word to remember from this discussion. Interface between the different levels of components that go into the system, but also interface between different disciplines, going from physics to engineering to neuroscience, that all have to come together and contribute to making this happen. So thank you so much to our panelists, and I will turn Now to a few specific questions we have been receiving from the audience, and I will read them out. And again, you can go in turns or volunteer how you would like to answer. So the first question is from the audience. We are approaching in the next 20 years or so the Shannon von Neumann-Landauer thermal limit. How can we address this limit? Big question.
So I have to admit, I don't have a very good answer. There are certain compute, areas where you talk about adiabatic computing, etc., but that has not really yet paid off. And I think there is, it's a very important question, what is beyond, but I think there is a lot of research which needs to be done specifically on this, and this is not yet done.
Mm-hmm.
I have to confess ignorance, but since the word thermal is in it, I think the strong interest in the last few years on quantum computing, which takes place at extremely low temperatures, has somehow revived the interest on low temperature electronics.
Mm-hmm.
And the performance of CMOS and electronics in general improves very fast as you come down to low temperatures. And so perhaps that is a path for addressing this limit.
Good. So I can go to, thank you for that, and I can go to the next question, which is, what are potential examples of CMOS compatible quantum computing designs, and where might we see these first being applied? Heike, I guess this is for you.
I guess that's for me, but I have to admit, I'm not really sure what is meant by CMOS compatible quantum computing designs, I have to admit. So I think what I want to add to this, I mean, we have quantum computing, which is based on the laws of quantum physics, and that's a very different way of computing. We can't go into detail. And then there's classical computing. What is definitely for the future is that these two computers, they have to work very, very well together. Because you have still a classical input side, you have the quantum computation, you have the classical output side, and you also have algorithms where you need an interplay between classical compute and quantum computing. And so the architecture and how classical and quantum works together, also with memory, is critical, and there's also a lot of innovation going into.
Thank you, Heike. Okay, so I see one more question. What are the key partnerships across industries that you envision being most critical to increasing adoption of more efficient computing architectures? Key partnerships across industries. I think that's the question, the key part of the question.
Okay, so let me take this. So yeah, as I said, in order to show improvement over incumbent, it needs to be a large system. And no matter what the new architecture is, that needs to interface with a large amount of logic computing and the data. So we need a dense memory and logic. So, and no single company possesses all the technology for that. So I think the partnership between logic, memory, and the new element, that needs to happen. So we don't think any single company can cover all of them. So the ecosystem is needed, and multiple companies having different expertise area needs to work together to enable such new architecture.
Mm-hmm. Thank you, Takashi. Would Heike or Jesus like to add?
I mean, what we see in the quantum computing area, for example, is that there is also to be the full ecosystem to be established, right? You need a cryostat, you need room temperature electronics, you need certain lines, etc., and all this. Also, the supply chain of this new compute area has to be created. That one company doesn't need to do everything in the entire system, but you can also have valuable suppliers which provide certain areas where the company you may not want to focus on.
Perhaps what I would like to add, the question is about partnerships across industries, but I think the partnerships have to go beyond and really include academia. I think there is a lot of innovation that is really needed here. We are talking about altogether new device classes based on new materials, new device physics. And that's what universities bring to the picture, that fundamental innovation that eventually, through the ecosystems that Heike and Takashi have mentioned, hopefully will reach the marketplace. So I want you to count universities as part of those partnerships.
Absolutely. No, yes. And I think that's a really very important point, because the very new ideas, leading ideas which you can test, there are the universities are really key. So I think we answered it now. Takashi and myself answered only the question which was asked, but I think really it's important to have a collaboration across all the different things, because it has everyone has its role in this in order to really have a fruitful and positive, successful outcome. And I think there are also very nice examples, like the SRC JUMP program, right, where you have different industries coming together, defining what the research is they need, and then providing also funding into a pool where universities can apply for these certain calls. So this is one mode of collaboration. I mean, we mentioned before there are different modes of collaboration. There are direct individual collaborations, but there are also for kind of how are they checking out what ideas are on the market, and then supporting these ideas and the early development. These type of private-public partnerships are also very important.
Right. The following question is somewhat related to that. How can we incentivize these partnerships across industries, but also between academia and industry? Like the SRC model you gave is one example, Heike, where the industry provides a pool of funds for academic partners to join the problem and work together. And that's a very helpful model. Are there others that you can recommend for the field to consider?
Well, let me comment on that model, which is a helpful model, but it can be improved. Right. And it can be improved in two directions. One is the treatment of intellectual property, which is these days it's becoming such a stumbling block to be able to work together, particularly across the academic industry line. And I think we just have to, particularly as we talk about very fundamental problems that are going to take a long time to eventually render industrial practical deployed solutions, we should just be willing to work in a open environment where we just put all our new findings open to the world at large. And then that eliminates one of the big stumbling blocks here, which is to find an IP agreement. It's such a big problem in these collaborations. The second one, and I hope this doesn't sound like whining, is this is very expensive research. We run very expensive facilities. We have very complicated equipment. It needs to be maintained by very specialized personnel. Our materials are expensive. What can I say? The research funds need to keep up with the real costs of the research if you want this to make a difference. So I would encourage, as companies look at working with us, to really sit down and listen to us as we put a budget together to understand why things are so expensive. But this is the reality of the situation. We cannot work around it.
Great, that's very helpful, Jesus. And Takashi, would you like to add?
Yeah. So to give a different angle, I think if we have one killer product or application out there as a result of the collaboration, it's naturally incentivized. So I think having some useful product or applications out there as a result of the collaboration is important first step, and then the rest of the step naturally follows. We need to think about incentive, etc. if it's very successful case. So we are in the stage of really trying to enable that, and that's very important to get this going.
To demonstrate some success stories that come out of the collaboration, to incentivize both sides more. That's what you're saying. Yes, very helpful. And perhaps also to get more support from the government to enable collaborations between industry and academia without IP restrictions, right? So Jesus mentioned about the IP-related challenges in working with SRC, but if some support or increased level of support come from federal sources that give more freedom for the academic research and the IP that may come out of it, but still enable collaborations with industry. That may be another model to call upon. Great. One last question I see is following up on a point that Takashi mentioned, that is the importance of having students trained and involved in AI, hardware, physics, materials, innovations, not only from software, right? And the question is, what changes or new educational programs should we start to enable this interdisciplinary thinking? Typically, we have traditional departments that educate in computer science or electrical engineering or physics, right? And one example that Jesus gave was a new joint program between neuroscience and electrical engineering. So maybe we should create and foster more of such interface natured disciplines between traditional disciplines. So if you can think of some examples to share.
Yeah, let me jump in. I actually feel very strongly about this.
Yeah.
You know, we have what one could call an existential challenge in the hardware disciplines, as they relate to microelectronics, which is the fact that undergraduate students are not choosing these disciplines to study, to do their majors. Students with interest in science and technology are mostly going towards AI, computer science. And this is a big problem because we're really starving the pipeline that would eventually lead to graduate school and to jobs and innovation in this area. So I think the biggest educational change that needs to be made, we really need to come up with meaningful, exciting educational experiences at the freshman level and at the sophomore level to attract the students with interest in science and technology to have a good look at hardware-based disciplines and to realize that they are immensely satisfying, that there are fantastic careers, and there are careers in which they can really shine. And I can give you as an example that this last fall, I ran a freshman seminar. So these are first-term freshmen coming to MIT. I ran a freshman seminar in which we brought the students into the clean room of the facilities of MIT Nano once a week for 3 hours over the entire term to fabricate silicon solar cells, to go through the process, to think through the process, to characterize them, to understand the models, and then to do it one more time, improving the process and improving the efficiency of the solar cell. The students were really delighted. So we not only got these 8 students, this necessarily has to be a relatively small group, really enthused about semiconductors and nanofabrication, but we also qualify them to be able to do research in the clean room facilities of MIT. So they can, if you want, sell their services to advisors now and bid for research programs as undergraduates to support research in hardware, in nanofabrication from their second term freshman year. I think it's experiences of this kind that we really need to introduce to attract more students to microelectronics disciplines.
That's a wonderful example, right? So giving them the first-hand experience that this field is exciting once you start working on it is a very good one. And so at the institution level, we can initiate more such cross-disciplinary programs. And maybe another point is in line with the spirit of this workshop, right? Computing has a tremendous impact on energy and sustainability. And this has to be taught to the students too, that there is a motivation to save the world, right? And computing is a big contributor in that direction. We have to come up with solutions to make computing more sustainable. And doing that only from software and algorithm side is just not going to work alone. So if we can convey that message to the incoming students, I think that can also help, because many students come with the goal to save the world, right? They want to do something impactful to save the world, and this is one of the important challenges that we have to overcome. So I guess it has to be told out there to the students as well.
I think, Birgit, that's a really very important message, because I think in the electronics and electrical engineering, physics, we are often not so good sellers of of the importance and of the impact of the work which is done in these disciplines. And here we have to, I think, adapt probably our communication-based or storytelling skills a bit better and really make the purpose which is there, right? Because without the semiconductor industry, without these things, we wouldn't have the video call, we wouldn't have a watch, we would not do anything almost now. And I think showing this and educating people about this, what the purpose is and what the impact is, that can also inspire more students to go into this field.
Yes, yeah, impact not only in terms of enabling advanced technologies that support our modern life, but also impact in terms of making computing more sustainable for the entire world. I think that message we need to communicate to them. And so this workshop is a wonderful opportunity for that. Hopefully we will have more of them. And that is time to end this very exciting discussion. So thank you so much, Dr. Ando, Dr. Riel, and Dr. Delalamo for joining us for this workshop and for this panel and sharing your ideas for our field. Thank you so much. And I will say that then this brings our second day of this workshop to a close, and we greatly appreciate everyone who has been involved in this workshop as a speaker, moderator, and participant. And the learnings from these past 2 days will be disseminated to workshop registrants along with some recorded elements. And so also please stay tuned to our next workshops in this space. So thank you so much for your participation.
Thanks. Yeah, bye-bye.
Thank you very much.
It was a pleasure. Thank you very much, everyone. Bye-bye.